hello everyone. Yanis, congrats on the first. Good to see you. It's been a minute, but I'm starting off my stream with tea again because I was running late. Which, I used to start basically every stream with tea because I was always running late, but... just waiting for the YouTube stream to get up. Why does it always take so long? Okay, there we go. So I thought I'd start off the stream at least with looking at some Project Euler. And try and find a question off here. I'll wait to see if there's a question from someone who pops up in chat. I kind of want to get past the first difficulty stage. Yeah, so let's like... Just do a 10%, because these difficulties are pretty subjective. Some of the 10% are easier than the other 10%. I'm probably going to stick to ones with more, like a higher number of solves. What's a path sum? Sorry, I forgot to mute for that. Yeah, this is like a simplified... I was watching FizzBuzz's stream, and like this is like a simplified version of like the knapsack problem that he was working on. Yeah, I remember looking at this one before, and not being sure how to make an algorithm for this. But I could try to just look at the knapsack problem and see if I can apply it here. Because I think it's the same thing. Oh, I mean, we don't have this constraint. That's right. That is a difference there. But maybe there's still something helpful here. Hmm. Six hose, 1, 2, 3. Okay, at least the names for those bots are getting funnier, but I still don't appreciate it. I feel like it's probably a better term for the to look up than the knapsack problem. Hashtag murder the bots. Yeah. Like, I was even thinking about making, like, cheap viewers or something a banned phrase, but... Well, actually, that would probably work. It would stop people from, like, joking about it. But I have to, like, they do cheap viewers, they do... best viewers, right? I don't know. I have to do, like, a new thing every time they invent a new phrase, I guess. Maybe you are a bot cheat. You know, Yanis, you need to put more value on your viewing, all right? I think that you could call yourself an expensive viewer if you know, just increase your prices a bit. The file they give really isn't that big. You don't have to be that, optimal here. Advanced viewbot with AI-generated text responses, exactly. Scorpora, cheap viewer here. Ugh. No, everyone here is a priceless viewer. Not even expensive. That was the wrong word. Priceless. Hey, Poloshan O'Reilly, how's it going? I'm already out of tea with my mug away. Okay, I'm doing good too. Thanks for asking. And hey, Coco. The more I look at it, the more I'm tempted to try to remember how the hell to write a recursive program. My coding skills are embarrassingly bad, and recursion is one of the things that I've really forgotten. You usually, like, the starting formula begins with your stop condition. Function. You're going to preparatory class next year. What do you think I should train? What does preparatory class mean? Like, I'm not sure. Maybe that means, maybe it's like a thing specific to your country, or like maybe like what type of math are you doing, or I guess what type of like education, or maybe even like what age around about you do it, something like that to. Add to something like that. Something like that, Coco. Like 18. So maybe is it like an entrance exam for or preparatory class? Maybe preparing for university, maybe? Preparing for the best engineering schools. Interesting. And it's a class rather than a test, or maybe preparing for a test. Yeah, it's something where I imagine there's a specific resource for it, but I don't know off the top of my head what advice I can give you that would be helpful. And you, wow, 2 years and then you pass the entrance exams. Yeah, like maybe if you want to say like, if you, or even can link to an example of the math that you'll be doing or are able to describe it, maybe try and give you the next step. But I'm not familiar with what you're referring to. And hey, Madara, what are your views on Lund University? Is Lund University like is that the name of the university? If so, I've never heard of it. What number Euler is this? We're oiling 81 today. PE81.py. And we also need matrix.txt. I'm going to copy and paste their file because I don't remember how to get transfer files into my virtual machine here. This is, no. Okay, there's a slightly better way to do it than what I was just trying to do. Save link as. Oh, I already have this saved on my computer, funny enough, because I have attempted this before. Do you know Madaru? I don't know Madaru Uchiha, no. Copy. Paste. All right, that's our 80 by 80 matrix. Hard locked. How's it going? Hey, Lord Azen, what do I think about IITS? I don't know what that is either. People are asking my opinions on things. I had no idea what those things are. I feel bad. I feel maybe like uncultured. My GF is like the square root of -100. She's a perfect 10, but also a match. I've heard that before, but it's a classic. They're like MITs in the US, like IITS. Oh, I think I've heard people. Yeah, the Indian Institute of Technology, Florida, as you're saying. Yeah, I know nothing about Indian universities. Second toughest exam in the world is the JEE Advanced. I've seen a couple of the problems, and they're pretty insane, yeah. Yeah, sorry, Polishon, that we don't have more some advice for you, but it's a little bit hard to do it for like super specific things like that. Let's go Python and VS Code. Yeah. I'm a little bit nervous on this one because I'm probably gonna embarrass myself with how terrible I am at coding, but this seems like a good opportunity to try to relearn recursion. Why do you try PUC or question to maths and JEE Advanced? Because they're kind of insanely hard. The ones that I do the ones that I've tried, I don't really enjoy the math. You know, okay, I have an immediate issue here, which is how the hell do we Oh, see, I already have the... Oh, no. Okay, well, let's get rid of this file. Delete permanently. We use that for our matrix. Okay, where's my 99? I need to remember how do you import... Okay. I wonder if NumPy has a more convenient way of doing this. Can I import data as an array? That feels like something that NumPy can probably do. Do you know about IMO, the International Math Olympiad? I know a tiny bit about it, enough to know that I really hate the type of math that they do, basically. NumPy import text file as matrix. Yeah, it's in like I could definitely learn it if I cared to study for it, but the questions are just unnecessarily difficult. Because I guess they have to be, because you have to... Do you need some way to distinguish between, or maybe you don't, maybe people will beg to differ, but I think the rationale is that they have to be hard because you have to distinguish between a huge number of students. But I think that's the only reason why the questions are so hard. Like you don't really have to do math that insane for a lot of applications. Oh, look at that. np.loadText. Use calls equal range. Okay, maybe let's look up numpy load text. All right, see you, Madara. The default delimiter is white space. We have comma white space. Get rid of that. Right? No, we have only comma, no white space. Okay. So the file name is 0081matrix.txt. I'm afraid that it's not autofilling. It's not exactly a math question, Madara. Does porn affect mental health? I don't really want to get into a whole discussion there, but you know, just do it in moderation. And it's up to, I think, the individual to define what exactly moderation is, depending on the effect it has on them. Let's just see what that does. So this is scaring me that it's not. Yeah. How did I really wrote 2 lines of code and I've already gone wrong. How does that work? Oh, load txt? Ugh, my god. You're kidding me. Oh, I guess because of a txt file. You know Hindi? No, I don't. D type equals. Does it tell me my option for how you actually write a data type? That's a dangerous game, Adar. I'm not going to do that. I've had people ask me to say words in language I don't understand before, and it turned out to be not good words, so I didn't do that. What? Oh, well, maybe it's int. I mean, sure, int 64, why not? That's probably not even an important thing to specify, but delimiter is the potentially only other thing I want to specify. It's comma. Hey, Henrik, I'm doing well. How about you? So what is this going to do for me? Okay. What? Did I? Oh, no. Exit? No? I'm scared. Okay. We're back. Print matrix dot shape. 80 by 80. Perfect. Okay. Good to hear. Good to hear. So we've imported the matrix. Well, I guess let's verify a couple of numbers. 4455, 297, 5115. Okay. I verified 3 numbers, so I'm going to assume the entire thing is per. Well, okay. Let's verify the last few numbers too. 2571, 3406. Okay. Obviously, this is flawless, and I'm not going to check anything else because I don't have to. I'm just working on this Project Euler problem, but I need to get back on the screen, don't I? Can I fit this up here? Ooh. Oh yeah, much better. Look at that go. That way you can see the output too. Yeah, it's an 80 by 80 matrix, and the problem is now up there if you want to see what the idea is. So it's now time to embarrass myself and try to write a recursive function. Find a path. So we want, I think, an I parameter, a j parameter for row and column, and a sum parameter. I don't know if we actually are going to want to return sum, or maybe ij and sum, but for now let's just keep it like that. So I think the first thing you always want to do with the recursive function is say when you want to stop. So if I is equal to matrix dot how do you access the first element of a tuple? you do it like that. And I guess -1. I want to figure out when I and j are in that bottom right corner. Because I guess that's when we want to return. Otherwise, we want to call new functions. I feel like this isn't right. Python tuple. Okay, yeah, you can index it like an array, but they do count from 0. And j is equal to matrix dot shape 1 minus 1. Then we're returning some. That's actually give it 79, 79, and just 69. And I expect a 69 back out. Okay, we do get 69 back out, just to make sure that I got this shape thing right. So the program, okay, let me find path 0, 0, and 0. That's how we're gonna start this function. So the first two zeros are for the upper left corner of the array, indices 0, 0. And we're starting with sum 0, not sum 41. And so I think what we'd want to do is say maybe something like sum 1 equals find path. Oh, no. So I'm checking if we're in the lower right corner. We do need to check if we're in, or if we're on the right border, or if we're on the bottom border as well. But maybe let's not worry about that. Yeah, let's just make that 2 do. Oh hey, it even highlights the 2 do. Okay. Sum 1 is equal to find path. So now we're gonna go, I guess we can do I plus 1, comma j, comma I guess sum plus matrix. Is it where I am right now? I think so. Yeah. I, j. And we'll do a sum 2 to move to the right, or down. We just did to the right. J plus 1 is down. Doing solves revolutions question for volume and surface area. How do you remember the different formulas? Is there a trick or something? That's a good question. For some of them, I memorize it, or I know it intuitively. Some of them I do just memorize, though. Oh wait, no, I think these are in a weird spot, I think. They're in Calc 1 for some reason. I think I only learned about them in Calc 2. Okay, so for rings, or I think, no, it's not shells. For rings and like watchers, I just remember that the area of a circle is pi r squared, and the idea of basically just integrating a bunch of circles from one end of the function to the other is pretty intuitive to me to get the solid of revolution, where basically the radius is just the height of the function and the actual height of the function is the function value. So I already know the circle is pi r squared, and instead of a constant r, we have a function for r, and that function is varying from one end of the interval to the other, and that's where your integral comes in. So that's my intuitive way of remembering it for... I feel like they're not called rings, like discs, something like that, but washers as well, because you can take always the outer minus the inner, and yeah. The other ones, like cylindrical shells, it's really the same concept, you can. So actually, it depends. It's sometimes just called shells, but I kind of like cylindrical shells. There's something reminding you that's a cylinder, and this is the surface area of a cylinder without the top and bottom, I think, and that's what we want. Right, okay, so the surface area of a cylinder, it's a little bit weird, but basically this part of the surface area of a cylinder is for the sides, and the 2 pi r squared is for the top and bottom areas. But when we're doing integration, we only care about the sides of this cylinder because the integration kind of fills in the top and bottom for us. So I remember it's kind of like a weirdly simple formula where it's just the circumference of the circle, 2 pi r, times the height of the cylinder. And it's the same idea where your radius is now your x and your h is now your f of x. And imagine actually creating those cylinders is how I remember that if you integrate with respect to x, you get the solar revolution about the y-axis, which is backwards from rings and washers, because if you integrate with respect to x, you get the solid revolution about the x-axis. But that relationship is reversed for cylindrical shells, and that's why it's good to know both, because sometimes one is way simpler. So I imagine this very visually, and I just kind of happen to remember the important bit is the area of a circle for these first 2 rings and washers, and then the surface area of a cylinder for cylindrical shells. And then the rest kind of follows from just knowing integration, and basically how integration adds up all of those cylindrical shells, or rings, or washers, or what have you. Surface area, that one I just memorize, because it's annoying. I'm sure it's not hard to derive it if I cared to. They should be. If you're not being given a formula sheet, that's kind of a shame. I've done these problems so much that I have that intuitive feel for them. But 100% when I first learned this, I just memorized it. Right. I do remember that they're similar to the arc length formula. Because, like, this bit down here is just arc length. Oh. This is the surface area of a cylinder, nearly. Where you almost have, like, your circumference and your height. So maybe this is one where I'll be able to intuitively realize it at some point, but this one I do just memorize for now. Yeah, I want to say even for like the AP calculus test that we have here in America, which is when you're in high school and you're doing the class for college credits, I feel like you're given a formula sheet for that. Hey, Brian, how's it going? Yeah, so for surface area, I don't really have a trick. I just have to look it up. But for the volumes, they're a lot more intuitive to me. Do you prefer exams without formula sheets? Why is that, Yanis? See, you're not necessarily wrong. I don't know what the advantage to not having the formula sheet is. Then they don't ask convoluted, complicated questions. Yeah, I guess that's fair. It depends on the teacher, I guess. I definitely have had teachers that are like they don't give you things for free. Like if you're allowed to use a calculator, they'll make it harder. If you're allowed to, you know, use kind of resource to make it harder, which is fair for like an open book test or something like that. But I like being given the formulas just because I don't know. I don't think you should lose points if you just can't remember it that day. There's no formula sheet for AP Calculus, there's one for AP Physics. Oh, really? I might be misremembering that then. It's been a while. And hey, S Rusher, over on YouTube, a square painting surrounded by a 1-inch frame. If the total area of the mirror... Wait, is it a mirror or a painting? Either way, I think we can figure this out, but I'm just going to assume that the mirror and painting are referring to the same thing, and it's not more complicated than it might be. If we have any reflection weird stuff happening, then please tell me, but I'm going to interpret the problem in the simple way. Best practice for taking tests. If they allow a graphing calculator, don't use one at all and calculate square root 7.25 to 3 decimals by hand. Yeah, true. It's mental math. All right, so... Not drawn to scale. Not written to scale either. We're given the area was what, 100? 100. It's your closest known square root. Oh, for a brains thing? Oh yeah, you can estimate them pretty well, I guess. I'm kidding, I'm not. I remember having to do that. It's actually, you can get pretty accurate, like one decimal approximations with that way. So we know the total area of the painting mirror thing in the middle is 100. Oh, sorry, the total area of the painting mirror thing plus the frame around it is 100. We know that, I mean, I think we assume, we know the outside is a square, and I think we can assume the inside is a square. So I'll name them X and Y. Oh wait, we don't necessarily need them to do X and Y. Because if I just name the outside to be X, so like this right-hand inside is all of X minus that inch frame minus that inch frame. So we can say that this is X minus 2, and by the same logic, this is X minus 2. Oh wait. Yeah, okay, I think we're already nearly there. Because if the total area of this thing is 100, all we need to worry about, or we can figure out the outside width of the frame right now, because we know that x times x should equal 100. So x times x equals 100. That's x squared equals 100. Take the square root of each side. X is equal to 10, and I'm throwing out, it's technically plus or minus 10. I'm throwing out the minus because we're talking about dimensions here. So I'm going to say it's just positive 10. And since we already said that the inside of the painting mirror thing is whatever x is minus 2, I think we have an 8 by 8 painting mirror thing. So I would say my final answer is 8 inches by 8 inches. Just to make sure, like, remember the units, they don't like dock you points for a stupid reason. So I hope that helps you, S. Russia. And Clown Kid over on YouTube as well asks, what's the difference between rational and irrational numbers? That's a good question. Let's go back to the board. I'm going to erase this in like 10 seconds, so take a screenshot of this work. Actually, you're on YouTube, so it's really easy to just rewind it. I'm going to erase the work here. Okay. A rational number it can be written in the form a over b, where a and b are integers. And b isn't 0, because we don't want to divide by 0. So examples of rational numbers are 1/2. 1,000 over 10. They don't necessarily have to be simplified. If b equals 1, we just get integers. So 5 is a rational number as well. The other, and we can also have decimals, because decimals are really just fractions, but not necessarily any decimal. We could say that 0.3 is rational because it's the same thing as 3 over 10. We can say that 0.333, or like repeating, 0.3 repeating is rational because it's equal to 1/3. We can write it as a fraction. So what we find is that basically any fraction of integers and any decimal that is either it doesn't go on forever or it has a pattern after some point is rational. Just check chat before I keep moving forward. Okay, I'll look at that later, Yanis, because I think you're giving a complicated explanation. Let's talk about irrational numbers. And I think the definitions for this kind of vary. And it's probably, Yanis probably wrote one, but the one that I'm going to say is a real number that isn't rational. just for like a simpler that definition, when I say real number, I just mean there's no imaginary numbers, which if you haven't heard of them, don't worry about it. It's more or less, if it's not rational, it's irrational. And examples are pi, 3.14159 something, I think like 6, whatever. It's a decimal, but it has no pattern. It just goes on forever with no apparent pattern. E, Euler's number, 2.71. I remember Obi told me a trick for remembering that one that I forgot. If you haven't seen E before, don't worry about it, but it's a number very similar to pi. Irrational numbers come up a lot with square roots as well. So like the square root of 2. It's like 1.41 something. That doesn't have a pattern, and it goes on for forever. And I think those are probably some of the most famous examples of irrational numbers. There are probably some other type of irrational number that I'm forgetting. But the entire point, none of these can be written as a fraction of integers. They're just like, they're kind of oddballs. We're always using some approximation of them, so we can't use, the decimal goes on forever, so we can never actually use a number exactly. Unless you just use the symbol pi. So, Conket, I hope that helps answer your question there. If you want to ask me anything else about it, or if I wasn't clear, please let me know. If preschoolers knew this, they would have it easier in uni. That's true. Not realistic, though. Oh, Henrik, I didn't even notice that you posted a problem in the Discord. You have to do something, you're gonna ask more questions in a few minutes? Sounds good, Clown Kid. Let me bring this up. Wait, why am I doing this? Wait, no, I do want to do this. Is this a spiral? That's kind of fun. The spiral, it starts small and it gets bigger. I guess we're pretty restricted on pi, though. Calculate the length of the curve. And the curve is rotated one turn around the line y equals 1. Oh no. What? Alright. Let's start off with the arc length part. That's gonna be pretty formulaic. I think the surface area part will be too, but that's gonna be a little bit harder to visualize. There's a pretty clean formula for arc length with parametric equations. Henrik, are you here, by the way? Maybe I should wait to see if you're in chat before I go off the deep end here. Okay, this integral won't be so bad. I worked it out mostly in my head. Oh yeah. Okay. It seems like Henrik maybe isn't here. I'm still going to work this out, though, and if I have to type back to Henrik in Discord, then that's fine. So for part A, and I assume Henrik is really asking about part B, but let's work through part A first. So our parametric equations, x equals e to the t over 2 cosine t, y equals e to the t over 2 sine t, and we know that t goes from pi over 2 to pi. We don't care about inclusivity or not, but just to be consistent, let's make it match. All right, so the length of the curve is just going to be the integral from pi over 2 to pi of the square root of, let me just make sure I'm going to get this right, the derivative squared plus the derivative squared, right? Yes. Okay, it's not going to be as clean as I hoped. Ugh, they give us product rule? Oh my, I forgot we had to take the derivative. Okay. dx dt, we have to do a product rule. 1/2 e to the t over 2 cosine t minus e to the t over 2 sine t. Oh no. Oh, what a jerk. We're gonna have to square this? Oh, that's not cool. Ugh. I hope there's gonna be a trick here. Because this is gonna get ugly. So we do dx by dt squared, which is unlucky. Plus dy by dt squared, which is equally unlucky. I thought we would just get to do this squared plus that squared, and it was going to clean up so nicely. This does not. dt. Spectry 0.25 times 0.25. Well, 25 squared is 625. So you take that, you move the decimal to the left 4 times, so you get 0.0625. Quick math. Is that right? Oh, 625. Let's go. Gobbling up those points. What's happening with this integral? Besides evilness. We can take an e to the t over 2 out of each. We can take it out of the square root entirely. Oh, 1/4? Fractions. Yeah, you can make it 1/16 as well. I don't know what 1/16 is off the top of my head. I could have just said 1/16 though, and that's still the right answer, I guess. That would have been faster. Oh well. I have 25 squared memorized, so it's not really that much worse. Okay, so we would factor in e to the t over 2 out of this. Maybe I'll do this in 2 steps. What am I doing? cosine t minus sine t squared, like that, plus the t over 2, 1/2 sine t plus cosine t squared. Oh, no. Squared dt. So then we can distribute the squared to that factor into that, like this factor. Same thing over here to there and there. And then we just get an e to the t that we can then factor out entirely outside the square root. So it's going to get another 1/2 slapped right back on it. So I'm going to say e to the t over 2 all the way outside the square root. And then we're going to factor out those bad boys. Multiply out. My answer is also okay, I guess. Yeah, Yanis is doing some like crazy math that I don't understand, but I'm sure it's very interesting if you did. Okay, so we're gonna do this thing squared. 1/4 cosine squared t minus sine t cosine t plus sine squared t. I hope I did that right. I think I did. One-fourth sine squared t plus sine t cosine t plus cosine squared t dt. Okay. Nearly there. Sine squared plus cosine squared is 1. 1/4 cosine squared plus 1/4 sine squared is 1/4. So we already have a 5/4 out here. Minus sine t cosine t plus sine t cosine t. We have just 5/4? Wow. That does clean up. Catch up with chat here. Right there. But during the semester, I don't have too much time, and yes. Oh, okay, fair enough, Yanis. Well, I'll see you around. And hey, Corrupt, if it's up when you said to Zach, I don't think I know the answer. I pretend to have a math degree. I will currently say a little more. Fair enough. Brian? Oh, wait, oh, sorry. Yanis is saying see it's a Spetri. All right, Spetri. Good luck with the last few of your exams. And hey, Phobos, if I didn't say it already. I feel like half people I say hi to them twice, but I rather say hi to people twice than saying hi to them 0 times. Maybe I won't say hi to you once. I don't know. I feel like I'm going crazy. Hey, Zach. Okay, we're nearly through with part A here. You went longer than usual. I was looking on your stream. You kept saying how tired you were, and then you kept going, which is fair enough. Hey, Joel Letsepe over on YouTube. Is it maths too? I don't know what you mean with that question. The question I have on the board is like a calculus 2 question. I would call it. You missed the part A? Yeah, sorry, Jed. Got less than you usually do. Oh, fair enough. I think maybe we're in sync then. I didn't fall asleep last night until like 4 in the morning. As long as you're good, that's the important part. Okay, so this integral is boiled down really nicely. This is just a constant coefficient, so it can come out front. We get root 5 over 2. E to the t over 2 integrates to 2 times t over 2. I said the wrong thing, but I wrote the right thing. What? Oh my god. I tried to fix that too, and I made it worse, which is the story of my life. So what do we get here? Root 5 over, well, we can just make the 2's cancel. Root 5 e to the pi over 2 minus root 5 e to the pi over 4. And exponent rules don't really clean that up, do they? No. Okay, it's a positive number though, which is a good sign. Not necessarily that we're absolutely correct, but if it was negative, we probably did something wrong. Tax the family can't tax them too much mathematically. Exactly, yeah. Should recently come to appreciate definitions more. For example, finding a good definition for what a geometric object is basically an open area. Really? Like a polygon? Well, I guess a polygon would be a specific thing, and the geometry shape is probably more general. All right, so let's verify the answer to part A, and then we're going to have to look up what the formula is for part B, because I definitely do not know that. And once we're through with this question, unless there's another one from chat, I was working on this project Euler question before, involving finding the path with least sum. Training? Mm-hmm. It is. You sound like Jon Snow. August 24th is coming. Or I guess you sound like a Stark in general, I guess, not just Jon Snow. Winter is also coming. I mean, yeah. We have 1/2 e to the t over 2. Oh my god, it's gonna be annoying to write. I regret wanting to verify this in Wolfram Alpha. E to the, oh no, bad Wolfram. Okay. Squared plus 1/2 e to the t over 2, no, sine t, plus e to the t over 2 cosine t squared. Okay. I pretend to like middle school education currently. I'm excited for this competition slam down of the century. Yeah. No numerical methods barred cage match. Brian, we're gonna me and Zach are gonna have a competition on August 24th, a coding competition. Dr. Cook. Well, actually, I should shout out his stream. Dr. Cook. I think he's currently on a little break, but he's a relatively new streamer. He offered to make, I think, like potentially 3 to 5 problems for us to either race to solve them all first, or do like first to 3 out of 5 or something like that. And I think they're going to be inspired by Project Euler, but we didn't give I think that concise of directions. Yeah. Flexes and Ruby. All right, see you, Yanis. In Larenzi, I shout out Dr. Cook. There's another relatively new streamer who I want to shout out to, Fizzbuzz. Fizzbuzz, like that. He's been doing some really cool. At least when I saw him last, he was studying discrete optimization methods. But he also does like physics visualizations and things like that. Just two cool streamers there who I think people should follow. And hey, Eaterflow official. I probably said that wrong, but I'm currently trying different number sequences: 37, 13, 54, 52. What? Find the sequence of that? Those are weird numbers. I don't know if you'll consider it cheating, but there is a database of integer sequences that you can plug things into, and it'll tell you what it matches. I definitely don't immediately see a pattern there. Those seem pretty dang random. Solution is supposed to be 832, 105? I see 13, and that always makes me think of Fibonacci. 37 might be a Fibonacci too, I can't remember. I don't see the pattern in that though. 37, 13. Yeah, I'm gonna plug it into OEIS. I hope you don't consider that cheating, or I guess if you do, look away, avert your eyes. Let me link you to the site. That was a Super Smash Bros. Sound, wasn't it? When you hit someone with the home run bat? Okay, sorry. And anyway. They match transformations from the original query. So this doesn't directly match anything, interestingly. Yeah, exactly, Zach. Okay. I'm glad I'm not the only one. Oh, the TF2 Scout. Did it make the same noise? Oh man, I used to play so much Team Fortress 2. I can't remember what noise the Scout would make, though. I can explain squirts in just a second here. Is this... Wait. This is the first two sequences alternating. Is this two sequences in one? Here's a greater Bostonian. It's literally 37, 13, 54, 52, 71, 208, 88. It's two separate sequences, like, alternated together. So you want to read every other one. The first one are triangular numbers? Something like that? This one I have no clue. That doesn't seem like any. Oh wait, you're just multiplying in initial... What? So yeah, that's the best that I got for you, Eaterflow. That it's these two sequences combined. I don't know how you would find that on your own. Sorry about that. If you're interested in math streams in general, though, because I saw it's your first time chat, let me link a whole bunch of math streamers. Yeah, it's a pretty crazy one. Those are all... Everyone in that list does math help of some kind in there, so if you're looking for more, like, help when I'm not around, they're all cool people. Yeah, Clownfit, I was just working on someone else's problem first, but I can explain square roots. Yeah, let's do that now. So a square root, I don't need this before. Well, let me, 1 second, Clown, could I want to take a screenshot of this? I don't want to lose the work I have on the board. Oh, come on, YouTube stream. Okay, there we go. Put that in there. The current song is Forget by Dawnbore. Oh, it's me, but bored. I just have it set to, it's something really like Spotify. It definitely isn't exactly Spotify because that's against terms of service. But I'm playing the radio for the song The Gathering by Radar. Okay, so Conkin wants to know what a square root is. There's a geometric interpretation and I guess algebra interpretation. I guess we'll get both. But they kind of come out to be the same thing. Okay, so now I keep forgetting to switch out the ink in my blue marker. Just stick to the black one. Square roots. A square root is basically the opposite of squaring. And I'll explain what that means. So if you square a number, like let's say 3 squared, that means you do 3 times 3, and we know what 3 times 3 is, it's just 9. What a square root does is it goes from this direction to this direction. Like we started by going left to right, but we can also go right to left. So we could start by asking what is the square root of 9? And kind of the crappy part is that we just have to know that 3 times 3 is 9. Square roots are kind of difficult to actually solve for a lot of times. But the square root, it answers the question, what number do you have to square to get whatever's underneath the square root? So, the square root of 9 equals 3, and 3 squared equals 9. These are both like completely equivalent expressions here. Like they're saying the exact same thing. So there's a little bit of a trickier part where 9 is a nice clean thing to take a square root of. We call it a perfect square because we know that 3 times 3 is exactly 9. So we don't get any funky business. But we don't have to have a perfect square underneath that square root. What if we had a square root of 10? Here, we don't really know. Not exactly. We have to approximate it. That's the unfortunate thing, because you can't name any two integers that, one multiplied by itself become 10. These turn into irrational numbers, actually, going back to your previous question. It's going to be 3 point, I'm going to bet like 1 something. And you can kind of estimate what a square root is by looking at the nearest perfect squares. So I know that 10 is more than 9 and less than 16. And 9 and 16 I chose because they're both perfect squares. If I square root all of these numbers, we would get the square root of 9 is 3. Square root of 10 we don't know. the square root of 16 is 4. So we don't know exactly what the square root of 10 is, but we know somewhere between 3 and 4. It's going to be 3 point something. And I kind of assume that it'd be 0.1, but that's kind of going by feel. It might not actually be 0.1. That's kind of a quick and dirty way to estimate what a square root is. I should say one other thing, which is you're sometimes in a situation where you have an algebra equation and you end up in some situation like x squared equals 9. And I'm just choosing that as a perfect square to keep things simple. Now x can potentially be any real number. We're trying to find out which real numbers potentially satisfy this equation. So if you just take the square root of each side, I'll show it in a separate step. You are allowed to take the square root of each side, just like you're allowed to multiply each number or each side by 2 or add 1 to each side. You can take the square root of each side. So the square root of something squared, it technically cancels, but not that there's a catch. So, you know, you can cross them out, but the issue is that if we come over here and say that it's just 3, we've actually missed out on a solution. We do know that 3 times 3 is 9, so 3, it does work, because 3 squared equals 9. But there's a sneaky second solution that we've missed by doing this. Because if I do -3 times -3, that's also 9. So this is another number that when you multiply it by itself, you get the number that we desired back out. So if you take the square, if you're in a situation like this, where you have a variable and you're taking the square root of each side, you need to do a plus or minus, is the kind of rule that you can memorize. So we would say that x equals 3 or x equals -3. It's really easy to get to like forget that little bit and think there's only one solution with x equals 3, but there are 2 solutions there. 0.25 is a perfect square. Oh, true, yeah. Joel, it looks like you're asking about finding a partial derivative. Yeah, I can certainly do that. Just let me do the last bit of the square root explanation, and then I'll work on yours. And I did say there's a geometric interpretation, which is basically this. If you have an actual square with, just to go back to the 3 squared equals 9 example, if you know the length of the sides of the square are 3, well, you know the area of a square is a side squared, which it sounds stupid when I say it, but that's why we say it's a number squared. So the area of the square is 3 times 3, which is 9. But again, if we try to go backwards and we have a square and we know the area is 10 and we want to figure out what the length of the side is, that's when you need a square root. And you say x equals root 10. Now the issue with the geometric interpretation is that negative lengths don't make sense. So we would say that the area is 10, but it's also equal to x squared. We would take the square root of each side to say that plus or minus root 10 equals x, and we would throw out the solution with a negative sign because we don't have negative distances. So in this case, when it's a geometry problem, we do only take the positive one. Okay, I think that's the end of the square root explanation or discussion, unless you have any questions on that. Yeah, square roots are kind of tricky because we don't have a nice clean way to calculate them like we do for a number squared. Going backwards isn't as always easy as going forwards. And so Joel wants to find the partial derivatives. Ooh, I'm gonna need to clarify what this function actually looks like, Joel. Because the notation is a little bit hard to type on YouTube. Oh God, already off to a bad start. So you have a function f of x comma y is equal to, is this ln of x and then separately over here, x squared plus y? Or is this entire thing inside of the ln? That's my question. Like, is only the x getting natural logged, or is the entire thing? Oh, shoot. You said yes, but I asked you like 10 different yes or no questions. I'm sorry about that. I maybe saying yes to only the x being natural logged. Only the x. Okay, good. Thank you for clarifying. So I'm just going to put the x squared plus y in front to make it a little more clear to me that it's not getting natural logged. And so you want to find the partial derivatives, it looks like. X, y, and xy. So let's start out with f sub x. So when we take a partial derivative, we pretend that anything that isn't x is a constant when we apply our differentiation rules. You know, I want to rewrite the original function one more time. I want to distribute the ln x into each of these. So it's going to make taking the derivative a little bit easier. To me, at least. So when we want the partial of f in terms of x, or f sub x, we pretend this y is a constant, like a 2 or a 3 or whatever number you want, and we take the derivative of x. So this right here, it only has x, that's a product rule. So I'm going to start by deriving the x squared, so 2x ln x plus, now the original x squared times the derivative of ln x, which is 1 over x. And then we take the derivative of y ln x. Remember that y is basically a constant, so it's just going to stay there. And ln x derives to 1 over x. So y times 1 over x. So does that f sub x make sense? And it needs to be simplified a bit. But that's the main idea with finding a partial derivative. You treat everything else like they're just any old number. So I'd say that's our simplified partial derivative with respect to x. And then we can work, I just want to hear if that makes sense to you so far, and then I can work on the other partials you asked for. Yeah, exactly, Joel. Oh, and Henrik, I worked out part A of your problem. I had to erase the work, though. I can come back to it though, because I still have it saved. Okay. And hey, Takshio, I can look at that after this problem. But I'm still working on Joel's problem, and we'll look at the floor of sine of pi x. Okay, so now let's find the partial with respect to y. So let's go back to this right here, and we treat x like it's a constant and y like it's our variable. So x squared ln x, there's no y's in there, so it may as well just be any regular number you want, and a regular number derives to 0. So it'd be 0, and now it's y times ln of x. Well, the ln of x we're pretending is just a number, so y derives to just 1. So we actually end up with just ln of x. So that's what we get for the partial in terms of y. But the final part of the question was, what is f sub xy? So this is called a mixed partial, and as me learning this for the first time, I believe for anything you're going to encounter normally, well, actually, let me say what this means first. F sub xy means you take the partial with respect to x, and then you take the partial again, but with respect to y. So what we're going to want to do is take this thing and derive it with respect to y. But as it turns out, I think for any function you're going to encounter normally, I don't think it's always true, but I think usually when you're first learning this, you're not going to encounter anything that's too weird that this isn't true. You're allowed to do the reverse order too. You can do the partial with respect to y and then the partial with respect to x, and you should get the same thing. I'll show it both ways, and we'll see if it comes up to be the same thing, I guess. So f sub xy, that means we want to take our f sub x and do the partial with respect to y. So I'm going to write out the notation too. This means the partial derivative with respect to y of 2x ln x plus x plus y over x. That's our f sub x. So take the partial of this with respect to y. Well, that has no y's. That has no y's. So these both derive to 0. That has a y over x, so the y becomes 1, and we get just 1 over x. So simplify, and we end up with only 1 over x. And now just for fun, let's check f sub yx and see if it comes out to be the same thing. So here we start with the partial with respect to y that we got over here, and we take the partial derivative with respect to x. And look at that. The derivative of ln of x with respect to x is 1 over x. So they do match. I think there's some crazier functions where this isn't true, but for most things that you'll encounter in your normal calculus class, it is true. So let me know if you have any questions on that, Joel. Oh, it's ceiling? Good to know. I always get that mixed up. Corrupt, I have no clue how to do it. I'm sorry. I did just like look at it, but I just don't know. Okay. Shoot, I haven't seen Henrik talk in a second, so maybe. We've answered Jules' question, and instead we back to Henrik's, we'll look at talk shields then. So Takshio wants to plot the graph of the ceiling of sine of pi x and find where it's discontinuous. I think plotting the graph and finding the discontinuities are going to end up being the same thing. So it's an exaggerated ceiling. All right, so we're going to start with just the graph of sine of x. That's why I want to start this. And do we have a restriction on x? Like, is it between 0 and 2 pi? I'm going to assume that we're between 0 and 2 pi for now at least, but we can always just temporarily solve it for between 0 and 2 pi and then, well, 0 and 2. So I'm only going to write out between 0 and 2 for now, and then we can always extrapolate from there, I guess, is maybe the word. So ignoring the ceiling for now, I just want to plot sine of pi x. So it should have a maximum when, no, it should be 0 when x equals 1, because sine of pi is 0. Oh, this is not to scale, let me tell you that. It's a little more to scale. Oh my god. Terrible. All right, something like that on 0, 2, which is one period of this. Oh, between -1 and 1? Okay, we can do that too. It'll just look like that. Okay. So that's vaguely what the graph looks like. And we want to take the ceiling of this thing. So we only have 3 possible values because there's only 3 integers that sine of pi x ranges through, which are -1, 0, and 1. So when x is well, maybe let's go from left to right here. So when x is right at -1, we have exactly 0. So the ceiling of 0 is just 0. So I'd say we have a dot right there. The thing is, as soon as we get even a tiny bit to the right here, oh wait, we actually stay at 0. Because we're only gonna be at -1 for a split second here. Okay, so what's gonna happen, this is weird. Let me actually make this in red. What's gonna happen is we start at -1, we're at 0. And as we travel along, all these numbers are between 0 and -1. So the greatest, the ceiling of them is going to be 0 still. Until, that is, we get to x equals 1/2. Because sine of pi over 2 is -1 exactly, and the ceiling of -1 is -1. So we're going to have a dot here as we suddenly jump. Or an open circle here, a dot here. But then as soon as we move away from x equals 1/2, we go back up to 0. So between -1 and 0, it looks something like that, I guess, which is really strange. We can plot some Desmos after. Oh, you want to know how to convert sine of x to sine of pi times x? Yeah. And in general, how do you deal with the coefficient in front of the x? Oh, good. So yeah, before I keep on graphing the ceiling, let's answer that question about the period of sine. Okay. So I like... Really? There we go. This thing right here is the most important thing for dealing with sine. I'll drop the link in chat. Whenever you have multiplying the x, this b here, your period becomes 2 pi over that number. And you don't necessarily have to memorize this exactly either, but this is I kind of like seeing this. At least I think it's good to see that this exists. You have a bbx minus c. Oh, yeah, positive being to the left is weird, but yeah. Well, let me show how we apply that. So if we have x and y, I just want to plot just sine of x and then show the transition to sine of pi x. So I basically remember how sine of x looks like. Which is like that, over 0 to pi over 2, which is one period of it. And I start from this, and I then play around with it depending on the function that we actually have. If we have sine of x, that is a period of 2 pi. Now, if we go down here and we have sine of pi times x, well, pi is our b. Our new period is 2 pi over b, or pi. So the pi's cancel and we get just 2. So what I do now is, I remember, instead of 2 pi here, we're going to have just 2, because that's one period of just sine of x ends at 2 pi, one period of just sine of pi of x ends at 2. So I mimic this exact same graph, and I'm just going to change the numbers on the scaling here, to be honest. So just basically take all the pi's out of these. We're going to end at 2, and these are evenly spaced before it. 1/2, 1, 3/2, or you just remove the pi from each of these. Everything else is the exact same. It maybe would have been more instructive to draw them with more accurate scales. But what this factor of pi has done is it's taken this graph up here and compressed it. Because 2 pi is 6 point something, but we're now ending at 2. So it's shrunk by nearly like, or this is nearly 3 times as big. This ends at 2, that ends at 6. If you want to think about it like that. And that's kind of the more general interpretation I was saying, which is in any function ever, well, at least in like this context, if you take your x and you multiply it by something, you're stretching or compressing it in the x direction. So we've taken this function and compressed it by a factor of pi. And that's how we get that. If you wanted to do sine of like x over pi instead, you would be stretching it and multiplying another pi through all of these. And the same is true if you have a parabola. If you take all it, well, I shouldn't show it like this, right? Actually, no, that's fine. If you take all the x's and multiply them by 2, so instead 2x squared plus 2x plus 1, this would shrink that same parabola by a factor of 2, so it'd be half as wide. I kind of want to check that last thing that I said with the parabola, because that feels weird to put the 2's in there like that, but I think it's what you do. Whoa, Decimals looks different. Who cares? Homepage only. That's the default squared plus 2x plus 1. Okay. Well, wait, no. It shifted a little bit. I might have done the parabola thing slightly incorrectly. I don't know why that shifted. That actually might be okay. That might be expected anyway. And there's general rules for function transformations that are good to know. They can sometimes be I think I've looked at this site before for their explanation and I liked it. They can sometimes be hard to visualize, but there's a bunch of rules that you can learn about for how functions get transformed. Let me catch up with what you're saying. Okay, so basically find the new fundamental period of the function. Exactly, yeah, tech shield. Yeah, it's something like that. And let me show sine of x versus sine of pi x, so Decimals actually gets the scaling correct. Okay, so this is just sine of x. And looking at just that period, we go from 0 to 2 pi here. And then if I turn on the graph of sine of pi x in green, you can see it completes its first period exactly at 2. It's way shorter. It's really cool. Thanks. Yeah, no worries. Yeah, that's a much better representation of how the scaling actually changes. I do it the lazy way where I just change my labels and not the scaling, but drawing it by hand, you have to make some compromises somewhere. Oh, do you already know how to do the discontinuity part? I have to look at your other question, but Takshil, I haven't seen that fractional part function before, but are you okay with like the discontinuity part here? Like, do you need to see the rest of that, or are you okay with that part of the problem? You think you're just okay, cool. So before I look at your second question, Takshil, Akash, I haven't done a question from them before, so let me look at Akash's. It's 3 a.m. here, I'm a med student. If you wouldn't mind, tell me how to middle term factorize, my basics are weak. Yeah, I think I know what you're talking about. That's not the way that I usually do it. Let me see if I can remember how it works quickly. So are you maybe talking about like a quadratic, if you have something like x squared plus 5x plus 6, how to middle term factorize it? I think I can see how. It's not the way that I normally do it, but I think I can adapt it. Or I can adapt the way that I did the x method to be, yeah, actually that's basically what I do. Yes? Okay, cool. So if we want to, ooh, man, how do I explain this? I can see what the answer is going to be. Basically, the idea is to split this 5x up so that it gives us a convenient thing to factor here. So I think I have a hard time saying how, but I'm saying that we can say that 5x is the same thing as 2x plus 3x plus 6. And from here, we would group it here and here and factor out whatever we can. So from these first two terms, and I'll go back and try and explain this more in a second, but I'll just show the entire method through and then I'll try and talk about it more. Those first two terms, they just have an x in common, so let's factor that out. So that becomes x times x plus 2. The second two terms have a 3 in common, because 3 and 3 times 2. So let's factor that out. And the magic of this middle term thing is that we now see that there's an x plus 2 and an x plus 2, which we can factor out. So we take the x plus 2 out front, and we're just left with x plus 3. So that's how the technique would work, but finding this initial step is pretty dang, like, hard. Because you have to figure out how to break it out exactly right so you get that x plus 2 and x plus 2. Like, these have to match for this technique to work. And that's the part that I'm trying to figure out how to explain it. You can do it with a formula, yeah, the quadratic formula, but it's so lengthy. So yeah, Akash, that's the part that I'm kind of struggling on. I think I have half an explanation. Because you're right. The real hard part here is how do you know to break the 5x up into 2x and 3x like that? And so this isn't, I don't think this is necessarily my favorite method because of that reason. It doesn't, I can't figure out a good framework to tell you to approach this aside from whatever term goes with the 6, it has to be a factor of 6. So because we need to be able to factor something out of here. If we were to try to do, if I were to do something completely random, like I know that 5x is 1 plus 4, this doesn't really work because we get strange things if we try to do the factoring part. Like, these don't match. We can't really progress from here. So I'd say that whatever you break that 5x up into, whatever goes on the right side there, it should be a factor of 6. So the factors of 6, let me... Factors of 6 are 1, 2, 3, and 6. And from there, you are basically, until you've done this a bunch of times, you're going to have to just try things as the unfortunate thing here, which is true of the way that I do it too. It's just, there's a little bit of trial and error involved here. So, we could have also reasonably tried having like a 6 go here, but then we have to compensate because we can't just have the 6 there for free. We need to subtract. Oops. No, sorry. We need a minus x in front here because minus x plus 6x is 5x. This is actually nearly right, but not quite because x minus 1, 6, x plus 1. So this at least it. We completely get rid of the coefficient in front of the x from this step to this step, which is good. But we don't get the same exact thing still. So this is the type of thing that you'd have to try until you find a combination that works, is the unfortunate thing. But that at least gives a little bit of a framework to think about it, where you should look for factors of 6. Yeah, exactly that, Akash. And so it is possible that there are no such, there is no way to break that up. If you have like square roots or imaginary things. So you could try every possible combination just to realize it doesn't work at all. Six x minus, oh no, so what I did at the bottom is not the answer. That's an example, that's like an example of something that you might try and realize that it's not helpful. This piece right here is just an example of a trial and error that you might go through. This does not help. You can't really progress from the step. This part right here is how you would factor it properly. That is not right. It's important to see, but it's not. It's valid math, but it's not helpful math, I guess. It doesn't get you any closer to that factored form. Completing the square. Oh, I mean, it's not more of like a vertex form thing. The way that I like to do these, it's something called the X method or the AC method or something like that, where if you're given x squared plus 5x plus 6, you want something that multiplies, or you want two numbers that multiply to 6 and add to 5. So these are 1 and 6 multiply to 6, and 2 and 3 multiply to 6. There's no way to make 1 and 6 add or subtract. Well, you can make them subtract to 5, but that's not helpful. You can't make 1 and 6 add to 5. You can make 2 and 3 add to 5. So you can go directly from this, look at the factors of 6, and know that you should choose 2 and 3. That's how I would do this. Yeah, gosh, I hope that helps. And yeah, Abudaya, that's right. What do I do? By the way, maths. I majored in applied math with a minor in computer science. I have a bachelor degree. I'm currently unemployed though. Okay, so I Takshil, if you're still here, I can try your other problem. Still here? Okay, cool. No worries, Akash. This, I haven't seen this fractional part function before. Let me get the problem up on screen. No, I didn't say it just then, Obi. I'd like to apply to I'm hoping to apply this fall for a master's in math, and hopefully to go in fall of next year. I had a short stint doing a master's in software engineering that I dropped out because of COVID. And before that, I tended to apply for a PhD in math, but I didn't get to the school that I liked. It's been an up and down journey, me trying to go to grad school. I guess it's been down, but I'm still hoping that it'll be up. I'm still optimistic. Yeah, Takshil, I think I can figure this out. Stupid pandemic, yeah. So we have f of x, it's the ceiling. Sine of pi x times the fractional part of cosine of pi x. So this problem looks complicated. Oh, there is a complication. Okay. So all right. I was about to say that they may as well ask what the discontinuities of, like, instead of this fractional business, what if we just had like a 1/2 there? And it's not really going to affect the, like, that 1/2, it really doesn't affect the discontinuities. But it's not quite that simple because this could be 0 and it could knock this sine of pi x from 1 down to a decimal. So we need to be a little bit careful, but I think it's only going to have an effect in a couple of cases. And otherwise, it's going to nearly be the same thing as the ceiling of sine of pi x. So I'm going to do a similar process here. I'm going to graph the ceiling of sine of pi x. And I assume it's the same domain, -1 to 1. And I think we're on board that, I don't know, I shouldn't have done that. No, I'm just going to use, I'm not going to use red here. The graph of just the ceiling of sine of pi x is this. This is going to be important for the next bit. X is 0 to 100? Oh, geez. Okay. That's not actually much worse. Because we're still going to look at just one like period of this, and then we can always multiply it. Because the period of this thing, we already said from last time, the period of this thing is 2. The same is going to be true for cosine. So we just look at between 0 and 2, and whatever we get, we multiply by 50 to make it for the entire interval, I think. So for our person to start this problem, we're just going to pretend like we're between 0 and 2. You did say 0, 100, right? Not 1 and 100. Yeah, 0, 100. Okay. Yeah, I really like doing these problems visually. Okay. So I want my extra. So without belaboring the points, this is the graph of the ceiling of sine of pi x. So it's mostly 0, except at 1/2 and 3/2. So we 0 times something is just 0. So we really mostly just need to worry about 1/2 and 3/2. That's how I read this graph, at least between 0 and 2. We can extend this out to 0 and 100 later. So let's look at what the fractional part of cosine of pi x at these 2 points are, because we don't need to care about anything else because it's getting multiplied by 0. We know that 0 times something is 0. So f of 1/2 is the ceiling of a half times the fractional part of cosine of pi over 2. Oh, look at that. Cosine of pi over 2 is 0. The fractional part of 0 is 0. So we get 1 times 0 is just 0. So even at that x equals 1/2 point, it's going to come right back down to 0. Oh, you're saying 0, 100 not inclusive? Or at least the conventions are sometimes different for different countries. If it's parentheses, like you wrote there in chat, it's near the same thing, but it means 0 and 100 are not included. I don't think it makes a difference for this problem, though. I'll update it to match your equation there, though. But again, take like this parentheses versus bracket things with the grain of salt, because different countries do different conventions. Oh, okay, good. So it sounds like we have the same convention then. So let's evaluate this function at 3 over 2 now. So we said that sine of pi x is -1 there. Then we have the fractional part of cosine of 3 pi over 2. And cosine of 3 pi over 2 is 0. Would you look at that? this function is always, or sorry, this function is always 0. Because the only time the ceiling part isn't 0 is at 1/2 and 3/2. And right at those points, they're perfectly lined up so that the cosine part is 0 there. So this has no discontinuities. I'd like to confirm that because this problem is like, these can be a little bit funky. Oh wait, how would I confirm that? We can kind of eyeball it maybe. 99? Huh. How would you get one discontinuity? Is that multiplication in the definition of f? I think they mean f of 1/2 would be 1.0, not 1. Oh, really? Oh, did I misinterpret this? So, I thought it was maybe just some weird, like, it was just, you know, it's hard to type notation in YouTube chat. Is it actually, is this a decimal point here? I thought it was multiplication, but is it supposed to be 1.0 rather than 1 times 0? Same down here. I would get 100 discontinuities there though, which is weird. By my logic. Not 99, but it is multiplication, you said. Okay. We are multiplying these two functions. Huh. Does Desmos do fractional part? Oh, like that. We'd want to do sine. Okay. What? Wait. Oh no! I see my mistake. I got fooled by the negative part. Or I graphed the ceiling of sine wrong. Wait, so what do we actually have? Between 0 and 1, sine of pi x is, the ceiling of that is 1. Duh, of course it is. Okay, I graphed it wrong. Because I'm bad with the ceiling function, evidently. Ugh, okay. Okay. So right at 0, sine of 0 is 0. So we do have a dot right here. But as soon as we go a little bit to the right of 0, sine of pi x is 0 point something, so it shoots up to 1. And it stays at 1 all the way until we get to x equals 1, because sine of pi is 0. And then we stay in negative, like negative 0 point something, which ceilings up to 0, until we get to 3 over 2 exactly, where we go down to negative 1 exactly. But then we go down, then we go to the right a little bit and we shoot back up to 0. That's the issue. That's what I missed. I only did the negative part, and I assumed the negative part would match the positive part because of how the domain changed, and I just got mixed up. That's my bad. And we end with a closed dot there. Okay, that's what this graph looks like. I only did that part before, and I just made this part match that part, but that's not right. Okay. So now for this, I think we mostly need to be worried about when this thing is 0, I think. It's not as clean now, for sure. So I think the fractional part of cosine of pi x is to the same. It has the same period as sine of pi x. The period of cosine of pi x is also 2 pi. Let's start by graphing just cosine of pi x. Cosine starts high and it goes low. Now let's come down here and take the fractional part. Is the fractional part always positive? I guess no, it doesn't have to be. It's not 2, it's 1. Okay. The fractional part is always between 0 and 1? Oh, I didn't, oops, my decimals graph. I didn't update a part of it. Oh, wow, that's funky. Okay. So, when x equals 0, cosine is 1. The fractional part of 1 is 0. So I'm claiming we start there. But then as soon as we go to the right of x equals 0, we get a fractional part. And that fractional part is going to start high, like 0.9, and then go to 0. 0.999 something, and then go to 0 by the time x equals a half. So the first part of this graph, we have an open circle there, and then the fractional part is going to become 0 again, right there. Now when we go negative, this would be like -1 plus 0.1. So this over here is like -1 plus 0.9. So I think this is going to start high. Oh, jeez, this is... and I think it's going to go low again. I don't know exactly how the curve happens. exactly at 1, it's going to be 0 again. And then I think it's going to like almost like reflect over here. And then right at 3/2, we kind of reflect this part, I think. Okay, I think, let me verify that against Desmos. I think that's what the fractional part of cosine of pi x is. I think I got the concavity wrong. But I can live with that. Okay. Oh wait. Oh, this is for cosine of x, so I'm gonna look between 0 and 6. Okay, so this part I basically got right. This part I should have, like, let me actually draw it to match. That one's a little bit hard to tell how I made the curve going like up like this. It should have come down and into the right. There we go. Ugh. Okay. I think I don't need to go back to the computer for this next one, but I still need to think for a bit. Yeah, no, I would recommend actually finding the concavity. It's actually fine to have the wrong concavity for the sake of this drawing. We only really care when things are discontinuous or 0. Those are the parts that I'm really concerned about here. So like how they do between that, I don't really care about. Because like if you have a continuous chunk here times a continuous chunk equivalently there for the same x values, we're never going to get a discontinuity. So I don't care how it's shaped between there. I only care where these breakpoints happen. Interesting. Okay. So I should have labeled this. Now what I want to do is multiply this graph by this graph. So let's start at x equals 0 and go right to left. So 0 times 0 is 0. Now we suddenly jump up. Let's look at, we hit our next discontinuity at 1/2. So let's look between 0 and 1/2. This is always 1, which is nice. When you multiply by 1, you're not actually changing much. So between 0 and 1/2, we just have this thing repeated. Because we're taking that and multiplying it by 1, so it's just this. Similarly, between 1/2 and 1, well, this thing is still just 1. I don't mind pointing it with both hands. That's just 1, and 1 times something is that thing. So we're going to repeat this part of the graph too. And right at 1, they both agree on it being 0. So that's definitely included. Now between 1 and 3/2, well, this is a non-zero value. This is 0. 0 times something is 0. So between 1 and 3/2, we just hang out at 0. We like it there. Now look at between 3/2. Oh, wait. Right at 3/2, we need to consider that we have -1 times 0, which is still 0. So 3 over 2 itself, we still have at 0. Now between 3 over 2 and 2, we have 0 times something is still 0. Okay. So this is one period of the entire function. Importantly, actually x equals 0 is not included because it's an open bound. So this discontinuity right here we don't get for the first period. Every other period we do get it though. Would you have, oh yeah, okay, that's not a new comment. Let me check that graph though, because I obviously, I'm not on my A game right now. But we're nearly there and able to answer the question. Okay, good. Basically what I got. Drawn much prettier. So remember, all we care about here is counting the discontinuities. So the important thing is to distinguish between the ends of the interval in the middle, or somewhere inside the interval. So on this first period, we have a discontinuity at x equals 0 and x equals 1/2, which means that every time we start a new period, we'll have a discontinuity right at the beginning and plus 1/2 after the beginning. Notice we don't have discontinuity at the very end, which is important because we're also not including, or we're not including 100, but that doesn't matter here. Basically, how we can make our conclusion here is that to 0 to 2, there are discontinuities at x equals 0 and x equals 1/2. Therefore, for x belongs to 0 to 100, not inclusive, there are two discontinuities for 0, 2 times 50 for the extra length of the interval, and then minus that one discontinuity that we counted at 0. And that's how we get 99. I wrote 500, I meant 50. So that's how you do the last step there. And I hope this makes sense. That's a pretty challenging problem. Can you explain how you draw the cosine of pi x graph? Sure. This was the exact same process as I did for sine. Start with just remembering that the graph of just cosine of x has this scaling. And the same rule applies with the period of the cosine thing over here is 2 pi over b, the same exact way. 2 pi over pi equals 2. So the endpoint over here was 2 pi. That means the endpoint over here must be 2. So we take the same graph and we squish it horizontally. So the exact same process with sine works here for cosine. Awesome. No worries. Thank you for the question. Oh gosh, how many do you have? Last one? Okay, we can do a last one then. If there's someone else waiting to ask a question, I would have to ask you to wait, but no one else asked a question in the meantime that I see, so we got time. Okay. Oh gosh. All right, I'll take a hard look at that in a minute. Tech Shield. Super Statement over on Twitch. Hey, do you have any recommendations for books? Do you have any books as resource recommendations for learning real analysis? I haven't studied real analysis that in depth myself. I wonder if Zach is around. What I'll say is that if you're interested in real analysis, Zach or e to the 2i pi should be your best friend. Oh, thank you, Obi, for the book suggestions. I don't even know enough to know like what the gold standard is. So I guess Rudin has a book on real analysis. But if you're interested in something that's, Zach is studying real analysis, and he's going to teach a class live on Twitch on real analysis. Let me... Where is the most recent word on it? I guess it was right here. So, oh shoot, what's the command for it? Is it Zach Discord? Hey, let's go. So this is that's linked for Zach's Discord here. He's going to be teaching part 2 of his live real analysis class on Twitch starting on September 10th. This is the time in my time zone. For you, it might be slightly different. It's going to be on Tuesday, Thursdays during the like American evenings, I'll say, not knowing what time zone you're in. So it's a real analysis class on infinite series. It's part 2 of a real analysis class of the part 1 he did in spring. In general, he's really good at real analysis questions too, if you want to pop in a stream and ask. But he's also going to be doing, on Mondays, starting in a couple weeks, he's going to be doing some kind of real analysis catch-up for anyone who missed out on the first class. So I'd recommend you like take a look at those streams too. But yeah, if you're just looking for like an offline resource, I don't have a better suggestion than what Instant Books Pachinko there put for Rudin. But these like live Twitch classes I think are super exciting. So I like to shout them out whenever someone asks about learning real analysis. Yeah. And I would be remiss if you didn't ask about it, but for you or anyone who's lurking might be interested. There are two other classes that are happening right now on Twitch. One of which is complex variables being taught by Penn Center. The other is differential equations being taught by Simplex Pachinko there in chat. They're currently happening now. And let me get the link to the Discord there too. Is it? I think it's just Penn. There we go. Yeah. So that's a link to the Discord that I have open on screen here. Okay. So yeah, sorry, Super Sam, not to like overload you with like links and stuff, but I just think that those classes that are happening on Twitch are super exciting, so I like to spread the good word. Okay, so Talk Show, thank you for being patient with me. Let's take a look at your question here. No worries. So yeah, the only analysis that I know is from part 1 of Zach's class there, from when I took it. So I only know things like mean value theorem, fundamental theorem of calculus, like that kind of like intro real analysis type stuff. But even then, I didn't study from an official source, just from like, or not from like a written source, like a book. It was just kind of what Zach put together for the curriculum. God, who the hell knows what arc cotangent looks like? I guess we can probably figure it out. Let's not go to Desmos yet. So I'm gonna write arc cotangent because I hate cotangent inverse, like with the -1 up there. I think the notation is not clear at all, but just know that they're the same thing. Yeah, Territar. I just remember that, and that gave me some confidence in being able to figure it out without Desmos. Yeah, so what I'm going to combine Territar and Takshil, what you two said there. Okay, you also just like, oh, you don't like the arc notation? I just try to avoid using that -1 whenever I can, because what you're taking the inverse of can be so unclear. Or like, you know, what sense? Like multiplicative, functional, all that good stuff. This is gonna be a weird one. Let's at least figure out what the graph of arc cotangent looks like without a calculator. So let's start by graphing cotangent. Cotangent, it looks like tangent. Tangent has asymptotes at -π/2 and π/2. Cotangent has asymptotes at x equals 0 and x equals pi. And it looks something like that, right? Because x equals 0, it's cosine over sine, and sine of 0 is 0, right? Okay. So that's one period of y equals cotangent of x. And just to help me figure out how the inverse looks, this maps, or, you know, x belongs to, in this case, 0 to pi, and y is -∞ to positive infinity. So when you take the inverse, these two things are going to switch. That's what I wanted to see here. So these vertical asymptotes are going to become horizontal asymptotes. So we're going to have a horizontal asymptote at y equals 0. Oh, I shouldn't... One second. Dang it. No, I'm trying to figure out what like window I want for like this, like that. Okay. Y equals 0. Y equals pi. And we take this thing and we basically flip it about y equals x. So if x goes from 0 to pi, that means y is going to go from 0 to pi. Wait. But in which direction? Do we start high and go low, or do we start low and go high? That's what I'm trying to figure out. I think we start high. I think I'm doing the flipping wrong in my head, though. I think we start low. There should be a way that I can just figure this out, right? I think it's like this. How can I know that? If we take, what is cotangent of pi over 2? Or it's not, it's the EE, that's a bad one, because that's 0. Ugh. How about pi over 4? Pi over 4 should be a negative number. Negative 1. What the hell? I need to look at Desmos. Start at 0 pi over 2. I don't know. I think it's better to try to avoid using Desmos. Oh, I did it wrong. Because, you know, you don't necessarily always have Desmos when you're doing a test, but... Oh, I'm wrong on both counts. At least I was consistently wrong. That means I did the reflection right in my head. Really? Because I was just taking tangent and shifting it over, but it actually gets reflected as well. Okay, that's annoying. Ugh. That's why I got confused with the whole, like, negative number thing, I guess. Okay. Okay, so that's arc cotangent. So now we need to deal with the sine of the parabola. So does the sine function gives, I assume it's negative when it's negative, 1, or it's -1 when it's negative, it's positive when it's positive. If it's 0, you get 0 presumably? Yeah, okay. Now, I don't know what else you could possibly get. But, I think I see the idea. If we want exactly one discontinuity, let me just write down the definition of the sine function. Just confusing because I mean SGN. If we want exactly one discontinuity, I think you want to keep this thing as always 1, and then it just dips down to 0 at a single point, and then it comes back up to 1. I guess you could, in theory, also do it for -1, dip up to 0, then come back to -1. I bet either would work. But let's see, we basically want a parabola that is always positive, except right at 0, where it should be equal to 0. Or always negative except right at 0. So it's weird, they do -k. It's greater than 0 for all x except, well, we don't care where that 0 actually happens. We just want it to be 0 at any single point. I think this is what we want. And we don't care where that happens, because we just want a discontinuity. We don't care where the discontinuity happens. Oh, kx? Oh, there was a typo in the original writing on the problem. Okay. Oh, we've had some activity in the Twitch chat. Let me catch up. Pick a k that gives it one discontinuity. If positive ever except at one spot. Yeah, kx does change it, but hey, LT. And hey, Milk. Is it? I mean, let me update the problem text to correct that. It's -kx. I think what I said is still true, though. We basically want a parabola, something like that, where the vertex is right on the y-axis, x-axis. That's an annoying y-intercept to have, though. Aren't there? I feel like there's gonna be multiple solutions for k. Unless they somehow don't work with this parabola. No worries, Talk Shield. May happen. So what's special about a parabola with a single zero? It's a perfect square. Which the +1, doesn't that make it a lot harder? No, k equals -2, right? I'm just thinking x squared plus 2x plus 1 is x plus 1 squared. Which means there's a single zero at x equals -1. Which is fine, I think. So that would imply, if we want a +2 there, that means k should be -2. Because that would mean, going back up to this original function, it's equal to arc cotangent of 1 when x is not 0, and it's equal to 0. Oh no, the arc cotangent of 0, which I think is still, well, it's pi. We should do a check that this doesn't happen to be continuous, which would be painful, but it shouldn't be. Arc cotangent of 0 is pi/2. By logic of that's how I graphed it before, and I hope that I'm not wrong. And arc cotangent of 1 is something over here. There's no way this thing is continuous. I think k equals -2 is our answer. If k equals +2, oh, you're right, Alti, yeah. Yeah, that's a good point. It's strictly decreasing, so it's not continuous. And what Territar said is probably the more logical way of doing it without like just guessing like I did. Yeah, so ±2 works. They actually give you the exact same function, like in that term. The logic I used to guess, yeah. So I didn't do a very good job of explaining, so I got excited. But what we want is a parabola that looks something vaguely like this, because it has a single zero. And that single zero is what gives us exactly one discontinuity in the sine function. If we crossed, you know, positive to 0 to negative, that's going to produce two discontinuities. Because we're crossing like 2 times. We're doing like 2 jumps. So we just want to jump once and then come right back immediately. So it's basically one jump. Like the function is going to look something like that, more or less, without doing any scaling or axes or anything. So that's why I said we need a parabola that looks vaguely like that shape. And a parabola with exactly 1, 0 is a perfect square. You can write it as like x plus something squared. And any parabola that looks like that is gonna have this kind of shape. Or that like its vertex would be on the x-axis there. And so what I did basically is I took the parabola that were given, x squared minus kx plus 1, and I set it equal to just some perfect square. And we can multiply that out. X squared plus 2ax plus a squared. And we can do a trick here called equating coefficients, where whatever's in front of the x here must be equal to whatever's in front of the x here, and whatever the constant term is must be equal to the other constant term. So we know that negative k should equal 2a, and we know that 1 should equal a squared. So if a squared is equal to 1, that means that a is equal to positive or negative 1. And you plug this in over here, you get negative k is plus or minus 2. And then you can multiply each side by negative 1, which doesn't change much. So k is plus or minus 2. That's the algebra way of doing that. I did it intuitively, but you could show it like that. Hey, Neon. How does a single root give us one discontinuity? That's a good question. It's because of how the sine function is defined. The goal, if we have a single discontinuity, that single discontinuity either has to look like that, or it has to look like, you know, for some generic function like that. Like it has to be a discontinuity like this or this. And what I noticed with the sine function is that at a single point, x equals 0, we get a jump. And so we could have a discontinuity that looks like this at a single point if we take advantage of how the sine function is defined. We just need to name something that is always positive, except it's 0 exactly once. And we get a discontinuity that looks something like that, where it looks like a continuous function, but you take a single point out. So parabolas are nice because both ends of the parabola go the same way. So you could have a parabola facing up, and that means both sides of the parabola are always positive. And that's a really important property because any positive number gets mapped right back to 1. The only thing to do is to make sure that the very bottom part of the parabola becomes 0 right at a single point, to make sure that we get this one jump at the single point. Exactly, yeah, that talk shit. Awesome. You have some like tough but doable questions, so I appreciate you asking. No worries. Oh, and Alti, I hope your bubble thing went well. That I forget what the thing was called, but it was funny to just like see you stream that like super random game that I'd never heard of. Okay. You won? Oh, that's awesome. That's right, yeah. I didn't know that people were making modern NES games, but that's cool. Okay. So I didn't see that Henrik posted the problem at first, and then I kept not catching Henrik when he was typing in chat. But ages ago, Henrik did ask this question here. We worked out part A already, but we still need to do part B, and then I'm going to type back to Henrik in Discord. I need to see this graphed out, though. I think it's a spiral, but I don't know what exactly part of the spiral we have here. I have way too many tabs open. I kind of want the rest of them, though. Alright, let's see if I can figure out how to do parametric functions in Desmos. I should not try to guess this. Parametric functions. Right, you write it like a point. Okay. To sine t for pi over 2 less than or equal to t less than or equal to pi. Ah, we need to do that there. That's actually not so bad. But... Ah, what? No. Okay. Yeah, Suna. I mean, I'm not trying to do just the hard questions, but that's what people are asking. E to the t over 2 cosine t, e to the t over 2 sine t. Hey, Fenbox. Around the y equals -1? That's such a strange... Ian? Oh, 01? Thank you for the follow. Okay, so... Oh, it's a surf... Oh, what the hell? This is a hollow surface of revolution? Like, between y equals 0 and y equals -1, are we supposed to have a hollow bit? Could we just make that a cylinder? Oh, God. How does this work? Huh. Parametric function surface of revolution. Good old Paul. Golden ratio curve thingies? Oh, I mean, I could see it turning out to be... I think it's a spiral. It's not necessarily golden ratio. But if we, like, increase the bounds for t, we do get a spiral. I don't know specifically if it's golden ratio, but... it's definitely some kind of spiral. If this random solid of revolution turns out to be the golden ratio, I'm going to be a little bit mad, I'm going to be honest. I don't know why that would be mad, but it kind of does, you know? So what if we... Oh, man. Paul doesn't even go there. Paul only cares about the x or y axis. Do we do a translation, though? Like, if we want to rotate around y equals -1, isn't that the same as rotating around y equals 0 if we add 1 to the y? Could I just do this? Rotate it about y equals wait, are we doing y or x? Y. Yeah, y equals 0. And not worry about it? I'm still worried about the hollow part. How does that deal with that? I want to Google this. Let's keep Paul, but consider the parametric equations. The parameterized curve, my bad. Parameterized curve. X equals e to the t over 2 cosine t, y equals e to the t over 2 sine t. Except for the problems I once tried and failed hard. I might do the same here, but definitely trying. The curve is rotated about y equals -1. A surface of revolution is generated. God, I'm scared. What is this? That has to be a typo, right? There's no way that's just some crazy integral notation that I've never seen before. I mean, Neon, I'm trying to figure out if this gap is significant. I don't know how the equation deals with that, or like what we're going to get out. That's what I'm concerned about. I could just plug this into the formula. That's probably what they want you to do. I'm not confident, but I guess let's try it. It's the worst that could happen. We're rotating this red curve about y equals -1, and we want the surface, not the volume. I'm the only person who invented units. 30 minutes because I forgot to convert units. I think you're gonna have a pretty long list there, syntax error. It's every type of unit that, I mean, actually for the most part, the job's probably been done for you. So they're like, well, when was the SI system invented? Like inches and pounds, everyone who was involved in that is like long dead, like hundreds of years ago. Right, to do cosmology then, set everything equal to 1. I assume the SI system was pretty old. All right, let's just blindly plug this into the formula and see what happens. I feel like there's going to be something off, but what the hell? YOLO. Sometimes you just gotta send it when you do math. Okay. So I'm writing these notes up for Henrik, who I don't think is here. So I want to take the time to write things out a bit more rather than verbally explaining it. S equals 2 pi x ds. 2 pi x ds. Looks like a wicked exercise. Yeah. Can you convert to polar using r equals e to the t over 2? Ooh. That's a neat idea, Teratar. I bet you, I guarantee you could. I don't know if that is what Henrik is supposed to do. It might not resolve this issue that I still feel a little bit unclear what to do with that gap. I think the integral will be a lot simpler, but oh, you think it might make the rotating more obnoxious? Huh. I don't know, to be honest. I don't know how to convert the entire formula to polar, so I'm gonna go with like the thing that I know. That is a neat thought, though. Same as rotating +1 about the y-axis. I do think this step is important here, because I don't know how this formula, I don't know how to convert the formula to work for y equals -1, so I think we convert our equations to work for y equals 0. Yeah, I'd be interested to see how this works in polar. I don't know how this formula should look in polar, though. I probably could find it, but I assume that Henrik isn't supposed to do that, at least. Or the person who asked the question. Ah, frick. I figured out what dx dt and dy dt are when I solved the part A. I don't care enough to look at my image, though. Let's just solve it again. e to the t over 2 sine t plus e to the t over 2 cosine t. The 1 goes away. Okay. The good news is that the radical part is going to be 5 over... Oh, no! Wait, no, yeah. This matches the same thing that we had in part A, and the radical just became the square root of 5 over 4, or root 5 divided by 2. I have to take the square root of 4. So this isn't going to be so bad. Oh, the plus 1, it doesn't even matter. We only use x in the formula, and the 1 goes away when you take the derivative. Okay. This thing underneath the radical is 5 over 4. I should check the image. It's not that bad. Yeah, 5 over 4. E to the t over 2 times root 5 over 4, I should say. dx dy equals dr d theta. Yeah, that r always gets you, but that's what makes the integrals a lot, it's what can make a lot of integrals a lot simpler. So this stays the same. This is e to the t over 2 times root 5 over 2 by what I did in part A. Root 5 over 2 can come out front. E to the t over 2 becomes e to the t. We get one of those annoying integration by parts that cycles around. I'm going to look that up. I don't feel like doing that. I think there's just as much work to look it up. Too late. I'm already back in my chair. It's an annoying integral. I could just do the DI method, I guess, but I'm already here. I kind of want to keep that where it is. Wolfram, you are going to integrate e to the x cosine x dx. 1/2 e to the x sine x plus cosine x. Okay. Okay. All right, so what do we get here? We get e to the pi, cosine pi is -1, sine pi is 0, e to the pi over 2, cosine pi over 2 is 0, sine pi over 2 is 1. Oh no, why are we getting a negative? Oh wait, it might not be a negative number. We might be okay. Maybe. Are we okay? I don't feel okay. minus e to the pi minus e to the pi over 2. That's a negative number if I've ever seen one. Ugh. Oh, before? Oh no, I didn't even see that ulti. I wasn't even looking at chat. I think it's 2 pi. I mean, I was just blindly following the formula. It wouldn't be that bad to change it to y. Oh no. Wait. Y equals 0, as it turns out, is the x-axis. Oh my god. Okay, thank you, Ulti. It's not gonna be that bad to fix. That always gets me. Y equals -1 is parallel to the x-axis. You have to switch them. It makes sense, but I don't have to like it. Just get rid of all this. That's what I get for not checking chat, I guess. Okay. This thing. You're right. It doesn't make sense for that +1 to not matter. Okay, so that's... e to the t over 2 times root 5 over 2 dt. It's just doing this, taking it home part that is slightly annoying, but really not so bad. Especially if you let Wolfram Alpha do the heavy lifting for you. Okay. That e to the t sine t is another job for Wolfram. And that's 1/2 e to the x sine x minus cosine x. That thing integrates to... Nope. 2 times that. I think we're good. Hopefully. What did I write here? Oh, those are 2 parentheses. It's like t times 1? Like that? Wait. Make sure I'm not being corrected again. Okay, no. Okay. To the pi over 2. It's 2e to the pi over 2 minus pi over 2 over 2 minus 2e to the pi. This is some weird like quadratic but with e's. I guess just one more step and then I'm calling it my final answer. All right. Let's Wolfram that entire integral and see what happens if it matches. It's this exact same integral, but plot twist. We put a 2 pi e to the no bad e to the t over 2 sine t plus 1. Wait. What did you do, Wolfram? What is this? No. Okay. Wolfram Alpha is a fickle mistress. Sometimes with this math input mode. I think that's good. Yeah, Suna. Why did the pi cancel? It's nearly perfect. The only difference... Oh, here's the pi. They put it on the right side. Okay, I got it right, finally. It would have been a lot shorter if I remembered that y equals -1 is parallel to the x-axis, not the y-axis. So I used the wrong formula at first. I accidentally used this formula when I should have used this formula. But yeah. All right, see you, Suna. All right, now I want to take a screenshot of my whiteboard to include it for Hendrik. What a problem. I still don't know if that accounts for the gap properly, but that would be a really mean problem if they quizzed you on that too. Okay, so oh, this place has been looping for a minute. I need to get a new playlist going. 1 second. Here we go. What am I doing? That's not the one I want. Okay. So I have here the two images of the whiteboard. For part A and part B. Is similar to the normal formula. It's still annoying to remember. Is in part B, there is a gap between the curve y equals between the curve and y equals -1. I'm not sure how the normal formula I used deals with that. I assumed it's fine and used the formula anyway. If something is off, it's probably because of that. I want to do a third image to be more clear about what I'm talking about. Okay, I just took a screenshot, put it in Paint. Let's do orange. Oh God. Okay. We have the straight line tool. Let's use it. For surface of revolution, and deal with it, but I don't know that certain. Okay. Then what we're gonna do is one of these bad boys. Control A, Control C. Bring it over to Discord, paste it in. Okay. Hopefully that helps out Henrik. And hey, Run VJ, what's your question? Type it out there in chat, or you can put it in Discord if screenshots are easier. Get some water. Clear off the whiteboard. Oi, busy day. Goodbye, marker. Hardly knew ye. I need to clean this dang towel. Okay. Go grab that marker. Oh. Cheap viewers. Oh, Ron VJ, I would so much rather have an easy question. Trust me. There is no question that is too easy. There are many questions that are too hard. People are asking the hard questions, but I try to help people with the questions that they have as best I can. So if it's an easy question, I would love that. Well, I wait to see it. I'm gonna throw away my wrap. 1 second. Okay, so I'll switch over. I'm going to see your question. Preparing for a JE and from India. Oh, nice. Oh, you know what I need to do? I need to switch out the ink in my blue marker. Let me do that. I keep forgetting to do it off stream, so I may as well do it now while there's a slow part. I need scissors. 1 second. Oh wait, how do I do this? Okay, I need to hold the marker like with the point up so I don't get ink on myself. Push the new one in, and we're good. Blue marker's back online. Seribot? No, I never heard of Seribot. Yeah, you can put it there in chat, Ron BJ. Let me see who's in the viewer list. Yeah, I mean, I don't see like a Seribot in there either, so. I definitely, I never heard of Seribot, so I definitely haven't enabled anything like that. Oh, interesting. Let me write that down. Seribot. Okay. So I would see what Ron VJ's question is. I'm just going to keep on looking at this project Euler thing that I started like 3.5 hours ago. Just for that's something to do in the meantime. Channel live to prevent hate raids. You haven't been popular enough. Oh. I mean, I think Twitch has like a shield mode or something. I don't really know what it does, but I figure something like that happens, just like emote only mode or something for a little bit. Oh God. That's an easy question? Okay. That's I used to read that as an easy question. Let's see if we can figure it out though. So I'm going to assume the sum goes out to infinity, and we're not literally adding infinity into the sum, which would make it a lot easier, because we can just say it's infinity. It's free and reports to the community. Oh, interesting. First step, you can convert it to tan inverse, then create difference. How does cosecant inverse convert to tangent inverse? Is that possible? Oh. What? I haven't seen these formulas before. So we have cosecant x. I guess we can do 1 over x. Five, 65, 325. I feel like you're adding multiples of 60 to 5? No, or like, no. I don't know. Oh yeah, yes. That's what the answer is. The following sets of conversions should be fairly obvious. I guess if you draw the right triangle. Not obvious to me, but anyway. All right, let's apply this formula and see how it looks. Let's do blue since we just made it better. Do we have, so arc cosecant of root 5. Oh, that's the sequence. That's a good question. I thought you were asking an unrelated thing there, Fenvox, but yeah, what the hell is the sequence of integers while we're at it? Okay, you know what, let's 5 times 65. Oh, all right, good catch, Zach. That makes sense. Okay, so you're multiplying by 5, or but 5 times 13 is 65. So what's actually the pattern? I still don't know what the pattern is. That's the connection between the two, I guess, but like, multiply by 13, multiply by 5. $65 times 325. Oh, Teratar, that's probably it. If you're doing the last two numbers multiplied, so 5 times 65 is 325. The next one is 65 times 325, I guess. As terrible as that sounds, we probably won't throw over the first few terms, or hopefully we only have to throw over the first few terms. It's like Fibonacci, but with multiplication. And your first two terms are 5 and 65. Maybe. Okay, but if we want this formula to work here, we take x equals to 1 over root 5. 1 over 1 over root 5. No, 1 over root 5. So you get so this one, just trying to follow along with what oh my gosh, Ron VJ suggested. Well, yeah, I mean, I can see how to convert it to inverse tangent, Ron VJ. It's just, we were trying to understand what the sequence actually is. Like, what's the next term? Which I guess we figured it out, but like, that's kind of an important thing to know. Like, what will be the fourth term there? Okay, let's simplify these fractions, I guess, and I hope we get a cancellation with the radicals, at least some of them. So that's 4/5 square rooted, so you get 2 over root 5. That is 64 over 65. The square root of 64 is 6, right? No, 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 it's 8. Second time's the charm. Square root of 324? There's no way it's a perfect square, right? Or it's going to be something stupid like 18. Is 324 a perfect square? It is 18. Something stupid. I told you. So we get arctan of a half plus arctan of an eighth plus arctan of 1 over 18. That's the sequence right there. I don't know what to do with that. It's normally tan inverse 1 by 2. The first one is tan inverse of a half. Am I missing something for the other ones? Making a triangle? I don't see what we're gonna get that's different, but... Ugh. Let's take like root 65. Cosecant is like 1 over sine. So it's hypotenuse over adjacent. Or over opposite. Am I getting the wrong thing? That should be 8. That's why I'm getting the wrong thing. So this angle is the same as arctan or inverse tan of... So what's the difference? I'm getting the same thing. Maybe there's some... I don't know. Fairness 2 over 16. Why would I want to do that, I guess? Or how does it help us? Oh yeah, Fenvox, we had to use that the other day. I think you suggested that same one. It might help, I'm not sure. I can get telescopes. Hey, Brian. And hey, Trong. Two, 8, 18 are twice the squares. Oh. True. It's gonna be one of those super vague summation. I didn't mean like the other one we looked at that was similar. Evreka912, thanks for the follow. Piyush, yeah, that's probably a good idea. Just Googling it. What do we have? Square root 5 plus cosecant inverse. Oh, this is fantastic formatting here. Love it. That's not good notation. Sum is pi over 4? I can see they got that at the very end. I'm trying to... keep some of the terms pairwise and notice a pattern. First two terms, shouldn't they be tangent of 2/3, not arctan? Oh no, it would be arctan. That's probably the natural thing we're supposed to do next. Ugh, I don't want a video solution. They say the answer is 1. All right, well, let's try the sum of tangents. Arctan A plus arctan B. A plus B over 1 minus AB. Okay. So applying the formula to these two terms. I mean, what's the pattern here, though? Oh, okay, if we're thinking the pattern is twice of a perfect square, starting like, that's 2 times 1, that's 2 times 4, 2 times 9. The next one would be, I guess, 2 times 16. A half plus an eighth is 5/8. For 1 minus a 16th. So if this pattern is indeed twice each perfect square, 1 over 2 times 16 is 1 over 32. Oh, what the hell, dude? I don't want to do that math. With 18 and 32? Work for Wolfram Alpha right there. One over 18 plus 1 over 32. 225 over 288. What's 18 times 32 now? I'm not doing my mental math. 576. Okay, what do we get? Five over 8 divided by 15 over 16. 2/3. I think that's what Fenbach said. You didn't even do the second pair? Oh, the first. Oh! I did the wrong pairs. I see what you mean. You worry just about. You don't pair it like I did. You do just these two terms, you get the new arctane, then you bring in the second one. Oh, and it's going to be like a geometric series or something. The inside, and you just take the arctane of that. So 2/3. We start with 1/2, we go to 2/3. Maybe it's not geometric, but something. So we do 2/3 plus 1 over 18. 2/3 is the same as 12/18. So we get 13/18. Two-thirds times 18. That's not. What? 2 over 3 times 1 over 18. Oh, I did have it right. 1 over 27. Okay. 13 over 18 divided by 26 over 27. Arctan of 3/4. So we're seeing the idea is we need to figure out what series the 1/2, the 2/3, the 3/4 represents here. What does that represent? Or I guess this is a sequence. Pi 4 is apparently the right answer, yeah. Oh, wait. Yeah, it's a sequence, not a series. So instead of doing infinite sum, let's do the limit as n goes to infinity. Well, or inverse tangent of the limit. N over n plus 1. That's what we have. Because we start at 1/2, 2/3, 3/4. Yep. That limit is 1. So that's pi over 4. All right. I see. Ugh. RMBJ, if that's an easy problem, you call that an easy problem, at least for me, that's not easy. Wait, we have to show that, Fenlux? Oh. Do that induction? I'm good. I feel like this one doesn't even just do it intuitively. I don't know. Maybe they do want you to do the full-on induction, though. So use exponential notation to get the answer? Like, you went to complex numbers? Aren't the inverse trig functions logs? I don't know exactly how that works. I'm not that good with complex numbers. It probably works. Oh, okay. But you also got pi over 4 with your way? It's reassuring. Turn into a sum of logarithms. Oh, the insides will multiply. That's kind of neat. I'm not sure if RamVJ is still here, but if you are, let me know if you have any questions about this. It's I definitely wouldn't call it easy personally. In the meantime, I'll probably switch back to doing a little bit of Project Euler until Penn Center gets started. Personally, I would have gotten stuck finding the sequence. Yeah, Terratar, that was super weird. That's a... I wonder if that transformation from 1 over x to x over root 1 minus x squared could be used to somehow show the sequence that you pointed out with multiplying the last two numbers translates into, I guess it'd be an arithmetic sequence that we got down below. Arithmetic. I don't know. I don't remember how you pronounce it in that. I solved it in seconds. Oh, I don't think that was in seconds, but I also have the help of people in chat. That was not the first JE problem that I've been sent, and I've seen that weird tangent sum identity before. Oh! Okay, you are wrong, BJ. Okay. Well, glad to help. Oh, in 2 to 3 steps? Oh, yeah, I guess there's only a couple of big steps. The conversion, applying the identity, and then finding the sequence. Yeah, those are the three big things there, I guess. All right, so as a little bit of filler, it's been a busy day, so I would be surprised if someone came in and asked a question right now, but in the event that to spend a little bit of time working on something, let's go back to this project Euler that I did at the very start of the stream. Do I have Instagram? No, I don't. It's really just the stream and the Discord. Oh, that's not what I wanted to show. Good thing there wasn't anything important on there. That's what I wanted to show. So I was going to try to write a recursive function here. And it's been so long since I've done anything with recursion that, like, it's going to take me a while to actually work this out. Oh, you know what? I think the checking thing here, we don't have to do anything all that special. We just, if I is less than matrix dot shape of 0, then we can increment I. Ooh, -1, right? You're unable to log in. I'm sorry, I'm not sure what to do about that. Like, you can't get into your own account, or is the server link not working? I think about a -1 here. Because when we're on index, so matrix.shape of 0 -1 is 79. When we're on index 78, we're okay with incrementing it once. I think that's what I want. Then we'll do that. I think you should sleep now, sir. Your sleep cycle me affected a lot. I don't know if you're telling me to sleep or if you're going to sleep. If you're going to sleep, then I hope you sleep well. If you're telling me to go to sleep, it's like 5 in the evening right now. It's a little bit too early. Oh, you're telling me to go to sleep. No, I just hold my neck sometimes. Do we want to do... I guess the very last number isn't relevant, because it's getting added to both anyway. I don't know if this is going to add in the last number or not, based on how I'm passing in this. It is, I think. So can we do like if sum1 greater than sum2, return sum1, else return sum2? Would this work? I don't actually even know if this is going to be proper. Recursion's hard. Let's just see it and find out. Oh, wait, what's the actual goal of this again? Find the minimal path. Oh yeah, we're just finding the minimal sum, and this, hopefully we'll get that. Am I out of bounds? I can see it's yelling at me. I don't know why it's yelling at me. It... What? Previous line repeated 76 more times. Invalid index to scalar variable. Oh my god. Let's see if it works. Oh, hey. Well, sounds good, P-ish. I'll see you around. Hope you sleep well. And I appreciate the kind words. This might not be very efficient. I think recursion is famously pretty inefficient, and I thought the matrix would be small enough that we can just, you know, brute force it, but I don't know. Oh wait, my final path isn't going to be quite right unless I can't take the actual answer this thing spits out. I think because I need to do some plus matrix. Well, wait. Do I? Yeah, I need to do some plus matrix of ij here, I think. I don't really want to stop the program from running though. I can always just do that manually if it does spit out a number. Do I plan to come to India? Oh, I mean, I'm not opposed to or I would do it someday. I definitely don't have any plans to anytime soon though. Give you a tour of Taj Mahal. I mean, that'd be pretty cool to see. I'm a little bit nervous that this is gonna loop. I accidentally made some kind of forever loop here. How do you do this in Python? Teratar, yeah, I mean, I'm trying to write it so it's not particular to the size of the array that we're given. The algorithm itself, if it does work, it's extremely slow, and it might not work in the first place. Python concatenate integer. Really? Oh. Oh, just put a string on it? Ugh. STR of that thing. I feel like you should have put a string on it. Do you have a great coding skill? Do also do anything except... Oh, I'm pretty terrible at coding. I used to be okay at it, but I've been doing this to try to get better at it. You describe the path as a list of booleans where true goes down and false goes right. Sure, but how would that help us, Teratar? I feel like you were a software engineer. I majored in applied math and I minored in computer science. I've forgotten a lot of what I've learned. I've especially forgotten a lot of the coding stuff that I learned. I've been trying to pick it back up a little bit. My computer's humming. I can hear it going. It's definitely working on something. I mean, I would love to reduce the time complexity of this Teratar. I don't know how to get every single path, though. I think this recursive thing, in theory, will do it. I don't really know how to express... I guess if you're doing it that matrix way, you can binary count. Okay. Oh, I can kind of see that, I think. Yeah, we want every possible 80 times 80. Okay. This is probably garbage. So oh, you're gonna make me blush, Piyush, but it's like it's really early there. You should probably get some sleep. Okay, so yeah, I really like the idea of making an array. Oh man, how can we do that though? Like if we have an 80 by 80 matrix that we're given, and I want whatever 80 squared is as a length for my binary number, and we're going to keep adding 1 to that. How do we do that in code though? Actually, we have some constraints on this binary number. There's only certain binary numbers that are valid. Because, like, the binary number 1, that isn't a valid path. We would need some way to detect that. Okay, now it's getting hard again. It's probably something like where I got held up when I was trying to solve this like forwards rather than recursively. I love that idea though, because it'd be very simple to take an array of zeros and ones, multiply it with the array that we're given, and sum it. I do love that. That's very elegant, but we need to figure out a way to make those arrays of zeros and ones. So what I'm imagining, let's take it simple. Maybe 5 by 5? I hope that's big enough to flesh this thing out a little bit. So we want every possible path starting from the upper left and ending at the lower right. So could we maybe find some way to start by going down the bottom and going to the right, and eventually, like, kind of, I imagine like popping these corners out so that like this will be our first iteration. Our next iteration would be this. The iteration after would be this. And that. And that. And then once we're here, we would need to go back to this corner and pop that out. That seems hard to describe, but I think that would eventually get us where we want to go. All right, please don't ham it up too much, Piyush. I'm just trying to write some code. Trim them down by removing the ones which go outside the bounds. I don't know how to describe that though, Taratar, I guess. Syntax. I have a problem to make a light of a mug as possible. I kind of assume it's a cylinder. If my mug is just a ball with a top cut out. Huh, stupid book writer. Oh yeah, I feel like I assume it's harder than just like a normal like Calc 1 optimiz, or I guess Calc 2 optimization. Or even 3, I don't know. I can kind of see the connection though. Oh, it's okay. I was wondering if you had to involve like different materials or something. Yeah, I mean, some say that like a coconut with the top cut off is the best mug. Please just kind of cool it. I just kind of want to talk about math here. Or coding. How could I write this? This idea. Wait, what syntax error? I assumed you were like beyond doing just like Calc 1. Self-taught cut. Oh, okay, that makes sense then. Get someone in your school. That's fair. Two to 3 month calculus package in 2 weeks. Wow. I mean, hey, at least that means that if your school isn't too good at teaching it, that you're already good. What are you majoring in? I did every single exercise in the sheet. 50% was recommended. Oh. Just an overachiever. Still in high school? Oh my god. I assumed you were so much beyond that. I assumed like you already had a degree. Okay. You're already like ahead of the curve then. I don't know like if it's a country by country thing, but when I was in high school, I was going to community college during like the summers to do some extra classes. So that's something that, because like they take people who are under 18, so that's something that you can do. It's a good idea. Neon FX VFX asks, why don't you become a teacher? I don't really want to work with kids, and teaching at even a community college requires a master's, which I don't have, so. You have to stay in high school longer because you can't pass Swedish? The hell? So are you like going to school in Sweden and not Swedish, or what's the deal there? You're Finnish. You have to know Swedish if you're Finnish? Huh. Interesting. That's so weird. Like, when I was in school, they do require you to take a foreign language. You really don't have to be slightly proficient in it, though, to get by in the class. Or, like, you know, the bar is really low. It's like, I did, like, 3 years of Spanish, I think. Although, I wish I was better with Spanish, to be honest. Hungarian is a closer language to Finnish than Swedish. So it's not like learning Portuguese in Spain. Wow. That's weird. I would think that they're very similar languages, but I guess not. Is there any way to send Python code to in YouTube chat? Oh gosh, not easily. Yeah, if you're not willing to join the Discord, I don't know of an easy way for you to do it, Teratar. You're dyslexic and struggle with Finnish too. Oh, okay. Yeah, I mean, dyslexia is fair. Yeah, I mean, you can try like putting a few lines, or like, I guess line by line or something, but yeah, it does suck when you know you want to study, but they make you do other things too. I think it's helpful for a lot of students, but not every student. I want to start by that's a good question, Jed. I don't know what an edge map is, I guess, but my original idea to use recursion, if it does work, it takes longer than I have patience for it to run. Edge map, it might be the right word for all I know. So my next idea was to make a path matrix of ones and zeros and try to write some kind of code that would iteratively, like, you try it with this path first, then you take this corner and like flip it outwards, do the sum of that path, and then you take that corner, flip it upwards, do the sum of that path. You would only have to store it for the current matrix, so it's not like it'll be a ton of RAM, like my recursion would be. But if you have a better idea, please tell me. Teratar is putting a function definition. Let me see. Let me copy paste what Teratar put in the YouTube chat there. Oh God. What is that tab? Tabbing. Oh, okay, I see. Creates list that goes like that. Go through 2, 3, 4. Oh, the example on screen. That you must go through 2, 3, 4, 9, 6, or 630. Right. Every possible path has one of those 3. you know the quickest route to each of those three, then you can simplify the matrix. Oh. Wait. So, you know the quickest way to each one of those three, you can simplify it. Then it's not ON squared. I think I know what you're getting at. I'm just trying to figure out how you... Yeah, sure. Hey.
Hey, so this is just me spitballing here.
Mm-hmm.
So let's take, for example, let's just follow with that example. So we got that one diagonal, 234, 96, 630, running from top right to bottom left on that third diagonal in. There's one way to get to 234, so you know the shortest route to that immediately, right? You have to go right, and so you have a path length to get to there. You know the quickest way to 630 because there's only one way to do that. It's straight down, right?
Quickest way, right, yeah.
So you have to go 131, 201, 630. It's the only way to get to 630. But to get to 96, you could take either of those two routes, right? You could either go through 201 or go through 673. Obviously, the 201 is a better option. So now you can completely discount any path that goes 131, 673, 96, because that will always be inferior to the 131, 201, 96 path, right?
True, yeah.
Okay, so let's just take that one step further. Let's say to get to 537, there's one way to get there, right? It's whatever the path is to 630, and then you just take that extra step, right? And the same with 103 at the top right on the top row. You can only get there through 234. It's right, and you're there. Let's take a look at 342. So you can either get there through 234. We know what that length is because we calculated it last step. Or we can get there through 96, and we know the shortest distance to that because we calculated that last step. So whichever one of those is shorter, then we go from there to 342, and we've completely eliminated the other path as a possibility for anything moving forward. So all you have to do is consider each step along the diagonals, and there's only going to be two ways to get to that from the previous step. So it is a bit of a recursion. But you know there's only one way to get to the one above it, and there's only one way to get to the right because you've already eliminated all other ways to get to that. So by the time we get to 956, or let's take 37 for instance, how many different ways can we get to 37 if we, don't eliminate anything, right? We could go right, down. We could go right, down, 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 right, down, down, right, down, down. Right, down, down, right, down. Right, down, 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 right. So that's all the rights at the beginning, right? We've got, 5 different ways to get there? And then we have to do, what if we just go right once? And then we have 5 different ways to do that, or four additional ways, because it could be right down, and then you could go right, and you have 4 different, basically you see how many paths there are to get to 37. Well, if we've already calculated the quickest way to get to 121 and the quickest way to get to 524, then we only have 2 ways to get to 37. It's the quick way to 121 and then 37, or the quick way to 524 and then 37. Does that make sense?
I think I kind of get the idea here, but how am I don't see what to actually like store or like change or like I don't see how to implement it, I guess.
Okay, so if you consider every column and you number them, are you numbering 0 to n or -1 or 1 to n?
0 to n minus 1.
Okay, so 131 is at coordinate 0, 0.
Mhm.
So now you need to figure out the quickest way to any point where the sum of the coordinates is 1, right? So it's going to give you 0, 1, and 1, 0, right? So the quickest way to 673 is 131 to 673, because you have to come to it from the left. There's no way to come to it from the top. Right? And the same thing for 201. You know the quickest way to get to that immediately, because there's no way to come from the left. You have to come from the top. Okay, so now let's take the diagonal where the sum of the coordinates is 2, and that gives us 3 options. Again, 234, there's only one way because you can't come from the top. 630, you can't come from the left. But 96, you know the quickest way. You know you can either come in from the top or from the left. And you have to figure out which one of those is quickest. And you can say, okay, to get to here, we're going to take 201.96. 131, 201.96. That's the only way we're going to get to 96, because the other way is already inferior.
So,
right, so now we have one way to get to 234, one way to get to 96, one way to get to 630. Now we do the next diagonal. We have one way to get to 103. We have 2 potential ways to get to 342, but we know we can figure out which of those 2 ways is a shorter number. And then we're going to say that's the way we're going to get to here. We're not going to ever consider the other direction because we can get there faster going this other route. So at every node, you're only looking at 2 different paths to get there.
okay.
And then the number of nodes you have to check gets larger until you get to that primary diagonal, and then it starts to get smaller. So it speeds up because you're not having to consider, at the most you're going to have n nodes that you need to check 2 paths on. Well, it's actually n minus 2 nodes that you have to check 2 paths on. The other 2 are given.
Yeah, so I guess what I'm saying is like on the first path, we're going to physically we're going to take the 201, we're going to add the 131, take the 673, add the 131, and then we're done with that pass, and then go to the next one, and then with the 96, we have to do like figure out which one of the numbers to the left and above it are lower, and add that one.
Yeah, so basically, if you're tracking, if you create like some information about the, what does it ask you to do? Find the sum? The minimal
just the sum,
right? Okay, so
minimal,
once so basically, you're going to take 131 and you're going to leave that one alone. 673, when you process that, you're going to update that to say the total length to this node is 131 plus 673, and you're going to store that value. And then 201, you're going to store the value of 131 plus 201. Then you never care about 131 again because you've already figured that into the other 2 nodes.
Right. Okay.
So you never care about 131 again. Then you go to the next node, you're going to look at 234. The only node you care about is the one to the left of it, and you already have that sum. 96, you're going to check both of them, figure out which one's cheaper, and put it there. Put the sum in where the 96 node is, because you've calculated that. And then the same for the 630, you're going to take the 201 and add 630 to it. Now you've got those 3, and you don't care about any of those first 3 nodes again. 131, 673, 201, you don't care about them anymore because you figured that sum into the next 3, and you just keep stepping through.
Yeah, I like that. I think that's way more efficient than what I'm trying to do.
Right, because, at most, if you consider it's an n by n matrix, so you're still doing... Maybe n squared is not the correct operation. N squared is probably what we're looking at here, because you're going to check every node in the grid. So that means you're going to be doing an n squared operation, right? If it's 80 by 80, you've got to do at least 6,400 checks, because you got to check every node in there. But you don't have to check into the n. Maybe is what it is. You're checking basically 2 n squared, which is still order n squared. Because you're doing each node you check, you got to see what's the sum from the left and what's the sum from the top.
I'm sorry. The shortest. Can you say the question again?
So in every node, you only have to do 2 checks. What's the sum it to get here from the left? What's the the path length if I'm coming in from the left, and what's the path length coming in from the top? Pick the minimum of those 2 and store it.
Right.
And we have to do that on every node in the matrix. And obviously the ones on the top and the left are simplified because there's only one way to get there. So you only have to do one calculation there. But every other node in there, you're looking at that approach from the left and from the top. Because they're only allowing right and down. If they said you can move any way you want through this matrix, then that makes it a little harder because now you have to, like the 803, you might want to swing around the 803 if everything around it is really small.
Yeah.
But they're not letting you do that in this case.
Thankfully.
So that's probably the approach I would take on that. Again, I'm not 100% sure it's optimal, but I think it's significantly faster than calculating all paths.
Yeah.
Because I mean, you're looking at what 2 to the 80th or 2 to the 79th operations, right? Every
it's
node
80
you
by
go
80.
right or down. Well, but you're starting at 0, 0, and you're
okay.
making 79 decisions on whether you go right or down. So that's 2 to the 79th possible combinations. And I'm not really sure what was that. That's what's scientific notation on that? Million, billion, trillion, quadrillion, quintillion, 604 sextillion different possibilities of paths. That's not feasible. But if you're doing 80 by 80, that's 6,400 nodes, and you're checking 2 directions to each of those. You're basically doing 12,000 comparisons, which is significantly better than 600 sextillion.
Yeah.
I mean, you could certainly try it with the basic matrix you have here and see if it. And if you wanted to track some metadata, so you actually know what the path was, not just the sum, then you could actually store like coordinates or some kind of maybe a structure like down right, some kind of string.
yeah.
How did I get here? And then you could actually redraw the matrix and show this is the shortest path. And if your character's down, we move down. If it's right, we move right, and keep the number in the original matrix and highlight that however you can do that. So you could actually store, if every node is more than just a value, it's the actual value, the shortest path to this location, and the path to get here with the shortest path, directional to get here, or even a list of nodes that we use to get here.
That could be cool.
So that way you could actually, here's every node's got an x coordinate, a y coordinate, a value, a min path length, and then the shortest path, which is a list of nodes. So it basically self-referential. So you can really have some fun with this one.
Okay. It's just like I think it's like a 10% difficulty. It's like one step up from the minimum, which I was up
What
with.
do you mean 10%?
Like the difficulties.
10% of people solved it?
No. The difficulties go in percents, and this is like one above the minimum.
Oh, so yeah, okay. Which for this is problem 81?
Yeah, so difficulty rating 10%,
yeah.
the bar is like almost empty. So I think that's probably like I can't think of a better way at least.
I hope this wasn't this is just practice for your competition with. Who
yeah,
competition with Zach or with
Zach, yeah.
Yeah, okay.
Yeah, so I can just remember how to code in general, and
yeah,
hearing that this way to do it is helpful too. Also because they're gonna be based on Project Euler, I think, the problems that we're going into. So
yeah, I do a lot of this stuff on in C#. I need to go back and learn some more Python, but
oh, C#?
I develop in C# for a living, yeah.
Oh, okay.
Right. Do you have a question about C# or something?
Streamer.bot, if you want to write your own custom code, it makes you do C#, and I've never done it before, so I might have some questions for you when I actually try to do something with it.
What did you call that?
Streamer.bot. I'll type in the Twitch chat.
Oh, streamer bot. Okay.
Yeah, it's the bot that I use for most things.
Okay.
But I want to
Yeah,
see you like a dev for me. I might try to write code for it on stream or something, and if you're around, you can help me or something.
yeah. I mean, I know enough to be dangerous. Haven't done anything with streamer.bot specifically, so I'd have to kind of see what exists there and
Yeah,
how I would code that. But there's an API
I
that
just
you have
like
to use and all that stuff. So
the syntax, like the API stuff. I can try to figure
Yeah.
out.
syntax isn't too bad, but yeah.
Okay.
Well, anyways, hopefully that'll give you a little bit of, make it not quite so painful to watch it calculate
Yeah.
106 trillion different paths. But
Yeah.
it's a lot of these times these Project Euler things are more like, it's not about brute forcing it. Some of the early ones you can brute force very easily, but it's about finding that the trick to the puzzle.
Right.
Like how can you simplify the problem in such a way that it's not brute forced and it's more manageable.
Right. Yeah.
Cool. Well, I'll let you get back to it. I just saw you working.
Okay.
This like, ooh, this looks like fun.
Yeah.
I haven't been in my Python stuff in a little while. I still have it, I think.
Oh, okay. I honestly, I might have to raid Pen Center in a couple of minutes here, so I might have to wait until Thursday. But I'm interested in getting this one like nailed down.
Cool. Well, good luck.
All right. Well, thank you.
Catch you later.
Yep. Okay. So, sorry, Tartar, that I wasn't looking at your chats. It should grow at a plus b factorial, where a is length, b is the width. Oh, for your like path thing, or sorry, for the path thing that we're trying to do with going through each path. Maybe I'm always so bad with like the combinatorics, but I really like this idea that Jed kind of outlined. Actually, is Pen Center live right now? Oh, Phobos. Thank you so much, Phobos. How's your stream? I didn't realize that you were going. I really appreciate it. I'm probably only gonna go for a few more minutes until Pen Center starts up the class. But I appreciate it. And if anyone here doesn't follow Phobos already, please go and do that. Short and sweet, nice, nice. Finished the GRE tests, all of them. Wait, like the practice tests, or did you actually go and take them? The practice, okay, nice. Oh yeah, oh wait, you said tests, plural, and you're only studying for the math one, I think. That's awesome. That's a lot of studying. I really tried to cram for when I was trying to do it over a period of like 4 or 5 months, and you did it in 4 months? Oh my god. Yeah, you're just built different, or I'm a slacker, or both. Either way though, that's huge. Hey Stooky. Let me check if Pen Center's live. I really shouldn't solve this Project Euler problem, but Pen Center is live. Dang it. Okay, this will have to wait until Thursday, I think. Yeah, let's go right up to Pen Center, I think. So if you're here on YouTube, Tartar, and anyone else who might be here, I appreciate you all, but I think I'm gonna cut the stream off here. I'll be back on YouTube on Thursday, and hopefully we'll get this problem done then. But it was a busy like math day. Yep, see you, Tartar.